Hello there and welcome to Science for Sleep, where curiosity doesn't have to rush and the night can be a little softer while we let the wonders of the universe drift past at their own pace. Tonight we have a visitor, and not the kind that knocks on your front door or texts you at odd hours, but one that has travelled across the cold reaches of interstellar space to arrive in our solar neighbourhood. It's called 3i Atlas, a name that might sound like it belongs to a robot in a science fiction novel, but in reality it's a silent traveller, older than anything we know on Earth, moving through our skies for only a short time before it continues on its endless path. Imagine that, something born around another star, maybe shaped in the gravitational tug-of-war of alien planets, slipping past us now without ceremony except for the few telescopes that spotted it. Before we go any further, I can't help but wonder, where are you listening from tonight? Is it late where you are, or are you tucked away somewhere in the middle of the day, curious about something that happened millions or billions of years before either of us existed? It's a strange kind of intimacy, isn't it? You, there in your own moment in time, and me here speaking of something that doesn't belong to our star at all, yet for now, we both share the same sky with it. If you find this little nighttime journey soothing or intriguing, it would mean a lot if you left a like or subscribed. It helps this quiet corner reach others who might be looking for the same gentle escape you are right now. So let's take a slow breath and begin. 3 Atlas is what astronomers call an interstellar object, which is just a technical way of saying it didn't come from here. The 3i means it's the third such visitor we've confirmed, the first being the much talked about Oumuamua back in 2017, and the second being 2i Borisov in 2019. These are members of a very exclusive club because space is big. The spaces between stars are far emptier than most people imagine, and the chances of a wandering chunk of rock or ice actually passing close enough to be noticed are small. Even so, here it is, crossing our paths in the vast invisible lanes of the solar system, and the first step in understanding it is remembering just how unlikely this meeting really is. Think about the distances involved. The nearest star system to ours, Alpha Centauri, is over 4 light-years away. That's about 25 trillion miles, or, if you prefer, the kind of number that doesn't quite fit in your head, no matter how many times you read it. An object drifting between stars doesn't have anything to slow it down. No thick atmosphere, no roads, no traffic lights. Just empty space, a few stray particles, and the faint gravitational pull of distant masses. It can keep going for millions, maybe billions of years before it happens to wander near another star. That's the journey 3i Atlas has been on, a path stretching back so far in time that trying to point to the beginning is almost pointless. By the time we noticed it, it had already done most of the travelling it will ever do in our part of the universe. Its name comes from the survey telescope that spotted it, the Asteroid Terrestrial Impact Last Alert System, which goes by the much friendlier acronym ATLAS. The system's job is to watch the skies for anything that might come too close for comfort, and while 3 Atlas isn't dangerous to Earth, it still set off the excitement that comes whenever something interstellar is confirmed. Atlas detected it in 2024, already moving at high speed on a path that clearly wasn't looping back around the Sun like a comet from our own Oort cloud would. Instead, its trajectory was hyperbolic, meaning it's on a one-time visit, never to return once it swings past the Sun. That's the first clue to its alien origin. For a moment, picture the astronomers seeing the first data. It's just a point of light at first, nothing dramatic to the naked eye. But run the numbers, plot the curve of its motion, and the truth becomes clear. It's not bound to the Sun's gravity. This is a flyby on a cosmic scale, a brief crossing of paths before it continues outward forever. In those first hours and days after its discovery, telescopes around the world were turned toward it. Everyone wanted to grab as much information as possible before it faded from view. And that's the thing about these visitors, they're fleeting. By the time the wider world hears their name, their closest pass is usually already over, and they're heading back into the dark. When we call it alien, we don't mean it in the Hollywood sense. There are no silver saucers or blinking lights here, just the raw ancient material of another planetary system, untouched by our sun until now. But that's exactly why it's so fascinating. Every rock, every grain of dust in our solar system formed from the same original cloud of gas and dust 4.6 billion years ago. We've studied them, catalogued them, sent spacecraft to touch them. 3i Atlas is different. Its building blocks were forged somewhere else, under the light of a star we may never see with the naked eye, in conditions that might have been familiar or might have been utterly strange compared to our own. It's not a loud visitor. It doesn't announce itself with a brilliant tail like a bright comet streaking across the sky. To most of us, it's invisible without a telescope, and even then, it's just a faint smudge against the black. But in that smudge lies information, reflected sunlight carrying the signature of whatever it's made of, hints at whether it's icy or rocky, dusty or coated with darker materials. And in that sense, it's a little like meeting someone in a crowded train station and trying to guess their life story from a brief glimpse of their suitcase and the direction they're walking. Astronomers work fast in these moments because the clock is always ticking. Interstellar objects move quickly, and the Earth itself is rotating and orbiting, which means observation windows are short. The data collected in those early days of tracking will be all we ever get. With Oumuamua there was frustration. Its unusual shape and motion stirred debate, but it was already too faint for further study by the time those questions arose. With Borisov, we had a little more time, and it looked more like a typical comet, complete with a tail and a cloud of dust. Atlas seems to sit somewhere between the two, making its classification a little less straightforward. The way it reflects light could be telling us about its surface, how smooth or rough it is, what kinds of minerals or ices it holds, whether it's shedding material as it warms up near the sun. But light can also mislead. The colour might shift depending on the angle of observation, the wavelengths measured, or the thin veils of dust surrounding it. This is why astronomers don't just take one set of readings. They observe across multiple spectra, from visible light to infrared, sometimes even radio, to try and piece together a fuller picture. Of course, there's also the question of what happened to it before it reached us. Interstellar space isn't entirely empty. It's full of low-density gas, cosmic rays, and occasional dust. Over millions of years, these can subtly erode or alter a body's surface. It might also have passed close to other stars along the way, heating one side, stripping away lighter materials, or even nudging it onto the path that led here. Every pit, every crack, every faint haze could be the result of encounters far from our sun. And then there's the thought, what if it's carrying something? Not in the science fiction sense of cargo or machinery, but in the scientific sense of material we've never seen before. Organic molecules, exotic minerals, isotopes with ratios not found in our solar system. Even a few dust grains captured from its coma could teach us more about the diversity of planetary formation in the galaxy than decades of studying our own backyard. Unfortunately, it's too small and too fast for us to send a spacecraft in time. All we can do is watch from here, and maybe dream of a future where we can meet the next one up close. And that's the quiet irony of 3i Atlas. It's travelled for unimaginable ages, across light years of emptiness, to pass us by in a matter of weeks. We catch it, record it, and then it's gone again, fading into the same dark it came from. But for a brief moment, we're part of its story, and it's part of ours. The next time you look up on a clear night, know that somewhere out there, past the edge of our sight, it's still moving, still carrying whatever secrets it has, heading towards some distant future encounter that neither of us will be here to see. When something new appears in the night sky, it rarely happens with fanfare. There's no sudden beam of light pointing the way, no cosmic trumpet announcing that we should look up right now. More often it begins quietly, as a faint point of brightness on a wide field survey image, one dot among tens of thousands. The night 3i Atlas was first noticed, The telescopes of the Atlas survey were doing exactly what they were built to do, scanning wide swathes of the heavens, night after night, for anything that moves. Most of what they find are asteroids, near-Earth objects, or comets from our own distant reservoirs. But every now and then, something doesn't match the usual patterns. The computers running the first pass of data analysis spotted the faint trace almost immediately, a speck that shifted position between exposures. That in itself wasn't unusual. Asteroids do that all the time, but when the preliminary calculations came back, they didn't make sense in the way astronomers expect. The motion didn't fit a neat bound orbit around the Sun. Instead, the numbers pointed to something moving too quickly to be a long-lost comet returning home. For objects in the solar system, the Sun's gravity is the governing force. No matter how far they wander, they loop back eventually. But this one was different. Even at first glance, the software was hinting at something rare. Its speed and the shape of its trajectory were more like something just passing through, on its way somewhere else. That was enough to get human eyes on the data. Astronomers have learned to trust automated systems for the heavy lifting, but a potential interstellar object is worth a manual check. They looked at the images frame by frame, making sure the motion was real and not some trick of the equipment, an artifact from a cosmic ray hitting the detector or a faint glint from a satellite. The trail was genuine, and so, within hours, the observations were sent out to the Minor Planet Center, the clearinghouse for such discoveries, where others could verify and add their own data. In those first days, the sky wasn't particularly cooperative. Clouds rolled over some observing sites, and at others, the object was too close to the horizon to get a clear, long exposure. But little by little, as more observations came in from telescopes around the world, the path began to take shape. It wasn't just fast, it was on a hyperbolic trajectory, the mathematical signature of a visitor from beyond. This was the moment of recognition, the same one that had happened with Oumuamua and Borisov, but still just as thrilling the third time. Interstellar objects are like rare wildlife sightings. It doesn't matter that you've seen one before. Each encounter is unique, and you may never see another quite like it. The name 3I Atlas was assigned quickly. The 3I marks it as the third confirmed interstellar object. The rest of the designation comes from the survey telescope that spotted it, a small nod to the system's quiet but vital role in keeping watch. It's easy to think of these surveys as impersonal machines, but behind them is a constant hum of work, engineers maintaining the instruments, programmers refining the detection algorithms, astronomers checking the alerts that pop up every night. All of that effort led to a single moment when a speck of light on a digital image was recognized for what it was. Once the word was out, observatories with far more power than Atlas turned their gaze toward the newcomer. Large aperture telescopes in Hawaii, Chile, and the Canary Islands began gathering data. Every observation mattered, because the object was already inbound and would soon make its closest approach to the Sun before heading out again. The challenge was timing. Unlike near-Earth asteroids, which can sometimes be tracked for months or even years, interstellar objects are here and gone in a fraction of that time. The clock starts ticking the moment they're found. Astronomers scramble to book observing time, often in the dead of night, sometimes shifting entire schedules to catch it. A few lucky ones manage to get spectra, measurements of the light broken down into its component colours. Those spectra are like fingerprints, telling us about the kinds of elements and molecules present on the surface or in any dust or gas surrounding the object. Even from these early readings, there were hints of something comet-like, perhaps with a faint coma beginning to form as it warmed in the sun's light. That raised its own questions, because an active coma meant volatile ices were present, but the overall brightness suggested it might be smaller than Borisov, possibly more fragile too. The data also showed that it was tumbling, rotating in a way that wasn't perfectly regular. That's not unusual for small bodies in space, but it complicates the work of modelling its shape. The changing angles meant that brightness measurements could vary not just because of material differences, but because we were seeing different parts of the surface as it spun. Still, there were clues in those fluctuations. The pattern of brightening and dimming hinted at a shape that wasn't perfectly spherical, maybe elongated or irregular, though not in the extreme way Oumuamua had seemed to be. While the astronomers worked through their nights, the object itself was moving on, indifferent to the attention. It swept through the inner solar system at tens of kilometers per second, unaffected by anything we could do, obeying only the gravitational pulls that had shaped its path for eons. Somewhere far behind it lay the star system it came from, unknown and perhaps unrecognizable now if we could even identify it. Over the course of its journey, the motion of the galaxy itself would have shifted the star's positions, erasing any easy way to trace its origins. In that sense, every interstellar object carries a mystery that might never be solved. But there was still so much to learn in the time we had. Teams coordinated across continents to make sure gaps in observation were minimized. Amateur astronomers joined in too, their smaller telescopes still capable of tracking the object's motion and brightness. This is one of those rare cases where professional and amateur efforts merge seamlessly. Every piece of data helps refine the trajectory. Every image builds a fuller record of the encounter. The more the orbit was refined, the more certain its path became. There was no looping back, no chance of capture by the sun's gravity. In the near future, it would pass the point of closest approach to Earth. Not dangerously close, but near enough to give us the best view we'd ever have. After that, the sun's pull would give it a final slingshot, sending it out along a different hyperbolic arc than the one it arrived on. It would fade into the black, just another faint point lost among countless others. But unlike most of those points, this one would never circle back into view. During these early observations, scientists debated whether it should be classed primarily as a comet or an asteroid. The faint signs of a coma suggested some activity, but it wasn't dramatic. Its surface colour leaned toward the reddish-brown hues common in objects that have been exposed to cosmic radiation for long periods, a kind of space weathering that can darken and redden surfaces over millions of years. That matched expectations for something that had wandered the galaxy's interstellar medium, bombarded by high-energy particles and micro-impacts for longer than our species has existed. Some wondered if it might have been much more active in the past, its outer layers already stripped away by previous passes near other stars. In that case, we might be seeing a core that's been preserved under a thin crust, holding secrets about the chemical composition of its home system's early days. Even if those secrets remain locked away, the mere fact of its arrival gives us something precious, proof that planetary systems eject material often enough for some of it to cross vast interstellar distances and find its way here. As the days passed, each observation added to a growing archive that future scientists could study long after 3I Atlas itself had vanished from sight. The hope is always that new techniques, better instruments, or more complete theories will make sense of data that, at the moment, seems incomplete. With both Oumuamua and Borisov, that has already happened. Years later, researchers are still finding new insights in the old measurements. It will likely be the same here, as 3 Atlas settles into the collective memory of astronomical oddities we were lucky enough to witness. The night sky is full of motion that most of us never see. Asteroids spin, comets shed tails, planets crawl along their orbits, all too slow or too faint for casual eyes. The arrival of something like 3I Atlas is a reminder that we live in a neighbourhood with open borders, where the boundaries of our solar system are more like thin, invisible lines than hard walls. The galaxy itself is restless, and the objects in it are always on the move. Every so often, 2 of those paths cross in a way that lets us glimpse the wider reality beyond our sun's family of worlds. And while 3C Atlas will leave soon, its presence has already done something valuable. It's given us another data point in the story of interstellar travellers, another case to compare against the ones before it. The more of these we see, the better we can guess at the processes that launch them from their home systems, the kinds of materials they carry, and the likelihood that some might even ferry the ingredients for life across the gulfs between stars. Each new arrival sharpens the picture, even if only slightly. From the moment the alert went out, the work has been a race against time, but it's not the frantic race of chasing a vanishing opportunity. It's a quiet, focused urgency, the kind that astronomers know well. Careful measurements, shared data, coordinated observations. The visitor doesn't care about our deadlines, but we do, because the chance to study an object like this comes so rarely. And once it's gone, it will be gone for good, carrying whatever stories it holds back into the unlit spaces between the stars. The designation might seem technical, just a bit of astronomical bookkeeping, but in it there's a story about rarity and recognition. When the letters and numbers 3I Atlas appear in the official records, they are doing more than labelling a point of light on a chart. They are placing it in an almost empty list, the kind of list that takes decades or centuries to fill. That I in the middle doesn't stand for some obscure chemical element or a forgotten satellite. It means interstellar, and in the modern history of astronomy, that's a classification almost no object earns. The way objects in space are named is deceptively simple. Newly discovered comets and asteroids start with a provisional designation, a code based on the date they were found. It's a practical system designed for efficiency, not charm. If an object turns out to be something special, the name evolves to reflect that. In the case of 3I Atlas, the initial designation captured when and where it was spotted, but once its orbit was confirmed to be hyperbolic, the I was added to acknowledge its nature as an interstellar visitor. Only 2 other bodies in all of recorded astronomy had earned that marker before it. 1I, Oumuamua, and 2I, Borisov. That alone makes it notable, because if you think about how many telescopes have been watching the skies for the past century, the odds of finding even one of these visitors seem daunting. For something to carry the I, it has to meet strict criteria. First, it must be moving on a path that no gravitational pull within our solar system could have created. That's what a hyperbolic orbit is, a one-way ticket past the sun, never looping back. Second, its speed relative to the sun has to be too high for it to have started here. There are a few technical refinements to that definition, but the principle is clear. If it's not bound to the sun and it's travelling fast enough to escape forever, it didn't come from our system in the first place. The question then becomes, where did it come from? That's the kind of question that sounds simple until you try to answer it. The galaxy is in motion. Stars orbit the galactic centre, dragging their own planets, comets, and debris along for the ride. Over millions of years, those orbits shift. The stars themselves move relative to one another, sometimes passing close enough that their gravity pulls on each other's outermost swarms of icy bodies. A close encounter between stars can fling material out into interstellar space, ejecting it forever from its birthplace. Some of those objects will wander for eons, unclaimed by any star, until they happen to cross paths with another system. That's the likely story of 3I Atlas, though the specifics, the exact star system that launched it, are probably lost to time. Astronomers can try to work backward from its incoming trajectory, plotting the line it travelled before we saw it, then projecting that line far into the past. But even if you account for the gravitational influence of every major body in our solar system, the further back you go, the less certain the line becomes. Add in the fact that the stars themselves are moving, and soon you're tracing a path through a galaxy that doesn't look the same as it did when the object began its journey. In a few million years, the constellations we know today will be unrecognisable. Over the billions of years an interstellar object might have been travelling, any hope of a clear home address fades. Still, there are things we can infer. Its speed and trajectory suggest it hasn't been significantly slowed or deflected since it entered interstellar space, which implies it probably hasn't passed too close to many massive objects along the way. Its survival to this point also suggests that it's structurally intact enough to withstand the tiny impacts and cosmic ray bombardment that come with crossing the space between stars. It's likely been rotating for a very long time, each spin redistributing sunlight across its surface, slowly altering it through cycles of heating and cooling, though on timescales so long they're almost meaningless in human terms. That 3I designation also changes how astronomers treat it. There are countless comets and asteroids within the solar system, each worth study, but an interstellar object is a once-in-a-generation opportunity. The moment its nature is confirmed, it moves to the top of priority lists. Observing schedules are rearranged. Instruments are reconfigured to focus on the wavelengths most likely to reveal new details. The eye is a flag to the entire astronomical community. This is not just another comet, not another fragment of our own solar family. It is something from outside, carrying the chemical and physical record of a completely different origin. The knowledge gained from the first two eye objects has already reshaped some expectations. Oumuamua was strange in both shape and behaviour. It didn't have the coma or tail of a typical comet, yet it accelerated slightly in a way that couldn't be explained by gravity alone. Borisov, on the other hand, looked much more like a classic comet, with abundant gas and dust streaming off it. That diversity between just two examples told astronomers that interstellar visitors might be as varied as the small bodies in our own system, some rocky, some icy, some active, some inert. The arrival of 3I Atlas means we can now begin to see if any patterns are emerging, or if each visitor will remain a singular puzzle. When you hear third interstellar object, it's tempting to think of it as just the next in a sequence, but the sequence is so far from complete that each one feels more like an isolated event. That's why the naming is important. The numbering doesn't just identify them, it underscores their scarcity. It's a reminder that despite the billions of small bodies moving through the galaxy, the alignment of conditions needed for one to be detected here is vanishingly rare. Some have suggested that as our detection technology improves, we may start finding these visitors more often. Surveys like Atlas, Pan-STARRS, and the upcoming Vera C. Rubin Observatory are scanning the skies more frequently and in more detail than ever before. Each additional year of data increases the chances of spotting the faint, fast-moving points that mark an interstellar traveller. If that happens, the list of eye objects might grow from a handful to dozens or hundreds in the coming decades. But right now, it remains exclusive enough that each addition feels historic. That's why, in those first days after the designation was assigned, you could almost sense the shift in the tone of communications between observatories. It was no longer about confirming an unusual orbit. It was about making the most of the fleeting moment we'd been given. The data pouring in would be compared to that from the earlier visitors, not just to catalogue differences, but to begin piecing together a bigger picture of what interstellar space might be sending our way. In that bigger picture, the eye is shorthand for a vast, untold backstory, one written in a part of the galaxy we will likely never visit. The practical details of the designation also tell you something about the culture of astronomy. The names are systematic, unambiguous, and devoid of embellishment. That's deliberate. It keeps the records clear and avoids the confusion that can come with multiple informal nicknames. But behind that dry efficiency is a quiet awe. Astronomers know what it means to have an eye in a designation. They know it could be decades before another one appears. That sense of rarity threads through every observation, every conference call, every pre-dawn moment spent adjusting an instrument to keep the object centered in the field of view. Even outside the professional community, the news of a third interstellar visitor sparked a certain fascination. The public has a natural curiosity about things from out there, and the simple fact that Through My Atlas is not from our solar system is enough to make it stand out. The idea of something so old, so far travelled, passing close enough for us to study, even briefly, feels like a gift, even if most of us will never see it directly. And perhaps that's the real power of the 3i label. It distills an enormous, complex reality into a short code that anyone can hear and immediately sense that it matters. In the end, the mystery in that designation isn't just about where it came from or what it's made of. It's about the improbable chain of events that led to it being here now, in this brief overlap with our own time and place. The eye is both a scientific fact and a kind of cosmic reminder. It tells us that our solar system is not isolated, that the boundaries we draw are permeable, and that every so often something from the wider galaxy will pass through, carrying with it the fingerprints of a place we may never know. And in that brief encounter, we have the chance to learn not only about the visitor, but about the larger context we're part of, a galaxy in constant motion, full of stories that only rarely cross our path. When an object like this is first spotted, its earliest label is purely functional. In the case of 3I Atlas, the first designation was a string of letters and numbers based on the date and order of its discovery, assigned almost immediately so it could be tracked in the global database. That early name is a placeholder, meant for astronomers rather than the public. It's not meant to be elegant or memorable. It's there so that anyone looking at the raw data can know exactly which set of observations they're dealing with. In a field where countless new asteroids and comets are catalogued every year, precision matters more than personality in those first moments. But when the reality of its nature became clear, when it was confirmed to be on a hyperbolic path from beyond our solar system, its name shifted into something that would follow it for the rest of its recorded life. The new label told the whole astronomical world that this was not a regular object. The number at the front marked its place in the historical sequence. The letter I set it apart as interstellar. The last part connected it permanently to the survey system that first saw it. 3I Atlas became the official enduring identity in scientific records. This is the way the naming process has evolved over decades of practice. It's not about sentiment, it's about clarity. That's why 1I, Oumuamua and 2I, Borisov have similarly concise structured names. The first half of each identifies its rank and its interstellar nature, while the second part reflects its discoverers. In Oumuamua's case, the word came from Hawaiian, meaning scout or messenger from afar, chosen to honour the location of the observatory that found it. For Borisov, the name was taken from the amateur astronomer who spotted it. In both cases, the naming served as both a technical marker and a kind of quiet tribute. In the case of 3I Atlas, the second half of the name points not to a single person but to an entire automated survey system. Atlas, the Asteroid Terrestrial Impact Last Alert System, has its telescope set up in Hawaii and South Africa, scanning the skies for anything that might one day pose a threat to Earth. Its job is continuous vigilance, night after night, catching faint moving points long before they might ever cross our path. It wasn't built with interstellar objects as its primary goal, but the same methods that detect near-Earth asteroids also work for identifying distant travellers. The fact that an automated system was the first to see this visitor says something about the state of modern astronomy, about how much of the universe's motion we now track through instruments that never sleep. The choice to name an object after the system that found it is a way of acknowledging that collaborative technological achievement. In the past, discoveries might have been credited to individual astronomers peering through telescopes, making careful notes by hand. Today, more often than not, the first detection comes from a machine's unblinking camera, flagging something for human review. The people behind Atlas, engineers, programmers, scientists, share in that discovery, even if none of them were looking through an eyepiece at the moment it happened. The name is as much for them as it is for the system itself. Some might find the official name a little cold. 3I Atlas doesn't stir the imagination in the same way as a poetic title might. But scientific naming has its own kind of beauty, especially when you understand what each part means. The 3 tells you that you're looking at only the third object of its kind ever found. The I tells you it's interstellar, something from beyond the sun's dominion. And Atlas reminds you that it was discovered not by accident, but by design. By a system built to watch for things just like this, even if no one expected such a visitor on this particular night. Of course, official names don't stop people from creating their own. Informal nicknames often emerge, especially when a discovery captures the public's attention. Sometimes these names come from journalists, sometimes from the online community of amateur astronomers, and sometimes from the scientists themselves in unguarded moments. With 3i Atlas, there have already been a few attempts, some playful, some inspired by science fiction, others simply descriptive. None of these are official, and none will appear in the formal databases, but they exist in conversations, in forum posts, and in headlines. They're part of how we, as a wider public, relate to something so far away and so alien in origin. Nicknames tend to humanize these distant objects, even if they're just lumps of rock and ice. Calling it the Traveller or the Messenger gives it a role in our imaginations. The truth is that most interstellar objects don't have any mission beyond drifting through space, but attaching a story to them is an old human habit. We've done it for comets for thousands of years, interpreting them as omens, symbols, or visitors from the gods. In that sense, the modern nicknames are just a continuation of a long tradition, adapted to fit a world where we also have precise orbital data and high-resolution images. In the scientific world, though, restraint is important. Formal names are kept concise and factual to avoid confusion. Every piece of data about 3i Atlas will be filed under that name. The images, the spectra, the calculated path, it all goes into the permanent record tied to that designation. Years or decades from now, when new techniques emerge that might let us learn more from the old data, researchers will pull up 3i Atlas and know exactly what it refers to, without having to sift through multiple alternative names. That continuity is part of what makes science reliable across generations. The naming also marks a transition point in the life of a discovery. Before the designation is finalized, the object is a possibility, a candidate for further study. Once it has a formal name, it becomes part of the record. The data gathering doesn't stop, but there's a sense of permanence to it now. Even when the object itself has faded beyond our reach, the name remains as a kind of anchor. We'll know it was here. We'll know it was the third of its kind we've ever seen, and we'll know who or what first spotted it. In a way, that permanence is what makes naming such a quiet but significant moment. 3i Atlas will be gone from our skies in a matter of months, but in the archives, it will always be there, frozen in the state it was when we first met it. The name is a reminder of the time when it passed by and of the thin thread of observation that connected its immeasurable past to our brief present. It's a practical label, yes, but also a marker of an encounter that, for all its brevity, joins a very short and extraordinary list. And perhaps the simplicity of the name is fitting. After all, the object itself is silent, without inscription or embellishment. It carries no declaration of its origin, no banner announcing its presence. We only know it because we happen to look at the right piece of sky at the right time. The name, stripped of anything but the essentials, mirrors that simplicity. It's a reflection of what we truly have, a record of where and when we saw it, and the knowledge that, in a galaxy full of motion, this was the moment our paths crossed. By the time 3 Atlas was first recognized as something unusual, the light we were seeing from it was already ancient in a personal sense. Even though it was only hours or days away in astronomical terms, the photons bouncing off its surface had started their journey when it was still far beyond the familiar orbit of Neptune. They had left the Sun, travelled out into the cold edge of our solar system, struck the surface of a body no one knew existed yet, and then made the long return to Earth. All of that happened in complete silence, and without any awareness from us until the faint trace appeared in a survey image. There's something humbling about realising that by the time we discover an object in the night sky, it's already been there for longer than we've been paying attention. In the case of a distant planet or a faraway star, that light could have travelled for years, centuries, or even millennia. For 3i Atlas, the scale was smaller but still a reminder of the constant delay in our perception of the cosmos. What we call seeing is always seeing the past, and in this case, that past was not just a matter of minutes or hours, It was part of a much larger chain of events set in motion before there were people here to watch at all. The first confirmed images of 3I Atlas were not the kind of dramatic photographs that make their way onto the front pages of newspapers. They were sequences of small, faint points, each representing a slightly different position in the sky, recorded over a few minutes. The excitement came not from the visual spectacle, but from the realization of what those points represented. This was something moving quickly, too quickly to be a familiar member of the solar system. That speed, combined with its incoming angle, was the first clue that it wasn't from here. In those early frames, the object didn't have the clear halo or tail that casual stargazers associate with comets. It was just a dot, indistinguishable from a star except for the fact that it changed position from one image to the next. The Atlas system, which takes multiple exposures of the same patch of sky over short intervals, picked up that motion automatically. The software compared the images, spotted the difference, and flagged it as something worth checking. What happened next followed a pattern that has become familiar in modern astronomy. The initial detection went into a central database where other observers could see it. Within hours, requests for follow-up observations began to circulate. Time on telescopes was allocated. Teams in different time zones picked up the baton as the Earth turned, ensuring the object was tracked continuously whenever it was visible. Each new set of images added to the arc of its path, refining our understanding of where it was and where it was headed. This kind of rapid, coordinated response is a relatively new capability in human history. For most of our past, observations of the night sky were limited by location, weather, and the speed of communication. Now, a detection made in Hawaii can be relayed instantly to astronomers in Europe or Asia, who can point their instruments at the same target minutes later. The network is global, and for something like 3I Atlas, that speed matters. These visitors don't wait for us. They arrive on their own schedule, and the best window for study can close in days or even hours. The first light gathered from 3I Atlas by larger telescopes revealed just how faint it was. Even under good conditions, it required long exposures to capture enough photons to study. That faintness wasn't surprising. It's small, dark, and far away. But it did set a limit on how much detail we could hope to see. Unlike the large, active comets that sometimes grace our skies, shedding streams of dust and gas, this one would never become a bright spectacle. Its story would have to be told through careful measurements, not through dazzling visuals. Those first measurements focused on two things: brightness and colour. The brightness tells us about size, although not directly, because it also depends on how reflective the surface is. A large dark object can appear fainter than a smaller bright one. The colour, measured by comparing brightness at different wavelengths, offers clues about surface composition. Many objects in the outer solar system have a reddish tint, the result of long-term exposure to cosmic radiation that alters the chemistry of surface ices and dust. Early indications were that 3I Atlas had a similar hue, which would make sense for something that had been drifting unshielded through interstellar space for millions of years. From the beginning, the data suggested that the object was active in a subtle way. Slight variations in brightness over time hinted at rotation. A faint haze around it hinted at the release of dust or gas as sunlight warmed its surface. These were encouraging signs, because they meant there might be a chance to study its material indirectly, by analysing the light reflected or emitted by whatever it was shedding. Even a thin coma, barely visible except in long exposures, can carry valuable information about what's inside. The astronomers gathering this data were working under a kind of quiet pressure, not the stressful, frantic pressure of a crisis, but the kind that comes from knowing an opportunity is fleeting. Every night lost to bad weather or mechanical problems was a night that couldn't be recovered. The object would never again be as close or as bright as it was now. The fact that this was only the third confirmed interstellar object added an extra layer of weight to each decision about how to use the available observing time. The first light in this case was not a single moment but a gradual unfolding. Each new telescope that turned toward 3i Atlas added to the picture. Some contributed sharp images that refined its path. Others gathered spectra that revealed chemical fingerprints. Radio observatories listened for emissions, not because anyone expected a signal in the science fiction sense, but because certain molecules emit characteristic radiation when they are excited by sunlight. Together, these different kinds of light built the foundation for everything we would learn about the visitor before it slipped away. It's worth remembering that much of what makes these early observations so valuable is not immediately visible to the eye. The colours might look muted, the details might be little more than a smudge. But within those smudges are patterns, ratios and variations that can tell us about temperature, composition and structure. An astronomer looking at the raw data might see only a few faint lines in a spectrum, but those lines can reveal the presence of specific elements or compounds: water, carbon monoxide, complex organics. In that sense, the first light from 3i Atlas was less like a photograph and more like a coded message, one that required patience and expertise to read. As more of that light was collected, the first hypotheses began to take shape. Was this an icy body like Borisov, shedding material as it approached the sun? Or was it more like Oumuamua, with a surface hardened by time and space weathering showing little activity? The evidence seemed to point somewhere in between. There was activity, but it was restrained, as if the surface was releasing just enough material to be noticed without creating a dramatic tale. That in itself was interesting. It suggested a surface that was partly insulated, perhaps a crust of dust and hardened ice over more volatile layers. None of this could be confirmed right away, of course. Science at this scale is iterative, with each night's results informing the next night's plans. Sometimes the early interpretations are revised entirely as new data comes in, but the first light is always special because it sets the tone for everything that follows. It's the first glimpse of the visitor as it is now in our neighbourhood, under our sun's influence. No matter how much we speculate about its long history, this is the version we get to meet. It's also the version that will be remembered. The photographs, the spectra, the measurements. All of them are snapshots of a particular moment in time, one that will never repeat. Even if another object like it arrives in the future, it will have its own distinct properties and history. This one is unique, and the record we create now will be all that's left once it moves beyond the reach of our instruments. That awareness lends a kind of quiet gravity to the work, even for those who have spent their careers studying comets and asteroids. In the end, the first light from 3i Atlas was not about spectacle but about recognition. It was the moment when an anonymous point of light became a subject of focused study, when the numbers on a detection sheet began to tell the story of a traveller from another star. It was the point at which we stopped thinking of it as just one more moving dot and started to see it as something with a history, a trajectory, and perhaps even a set of hidden messages about the wider galaxy. And all of that began with a few faint images and the decision to look closer. Long before we caught its faint signature on our detectors, long before it reflected even a single photon of sunlight back toward our telescopes, 3i Atlas was already deep into a journey that had no fixed beginning from our perspective. Whatever moment set it free from its home star system happened so far in the past that the concept of when starts to blur. In the human sense of time, it might as well have been forever ago. This is the nature of an interstellar traveller. By the time we meet it, it has already lived through distances and durations we can only frame in abstract numbers. Somewhere, at some point, it must have belonged to another gravitational system. Objects like this are not born adrift. They start out bound to a star, orbiting in a cloud of debris, perhaps far beyond any inhabited planets. Many stars are surrounded by vast belts of icy material, leftovers from the process of planet formation. In our own case, the Oort cloud extends trillions of kilometres from the Sun, a nearly invisible sphere of comets that rarely approach the inner solar system. In another system, somewhere in our galaxy, 3i Atlas could have once been one of those frozen bodies, slowly circling its parent star at an enormous distance. It doesn't take much to eject such an object if the right conditions come together: a close pass from another star, the slow gravitational tug of a massive planet, or even the cumulative effects of many small interactions over millions of years can shift an orbit until it no longer loops back to its star. Once it crosses that invisible line between bound and unbound, the object is set on a one-way path into the galaxy at large. From that point onward, it's no longer part of a single star's family. It becomes a wanderer, influenced only by the rare encounters it might have with other masses along the way. If we could somehow trace its route backward, we might see it pass the outer edges of its home system, slip into the thin emptiness between stars, and begin an arc shaped by nothing more than its initial velocity and the slow rotation of the galaxy. But even with our best simulations, that path fades quickly into uncertainty. Over the millions or billions of years such a journey might take, the positions of nearby stars change dramatically. Whole constellations shift into new shapes. What we think of as fixed points in the sky are themselves moving, each carrying its own entourage of planets, moons and debris. In that ever-changing environment, retracing the exact origin of an object like this is almost impossible. What we can say with confidence is that its path through interstellar space would have been quiet in the way only the cosmos can be. Out there, far from any star, the average temperature hovers just above absolute zero. The only light is the faint scattered glow of distant suns. No atmosphere slows a traveller down, and no magnetic field offers shelter from the constant drizzle of cosmic rays. Over time, that radiation subtly alters the chemistry of a surface, breaking molecular bonds, creating new compounds, darkening and reddening what was once fresh ice or pale rock. Every pit and scratch that might exist on its surface today is a record of that endless exposure. Occasionally it might have passed through the outer fringes of another star's domain, feeling a faint tug from a distant giant planet, or grazing the edge of another cometary cloud. But the odds of a close encounter are slim. Space is vast enough that even in a galaxy packed with hundreds of billions of stars, most of the journey would have been through nothing at all. Vast stretches where the closest object of significant size was measured in trillions of kilometers away. This is the environment 3i Atlas would have called home for longer than our species has existed. It's also possible, though we can't prove it, that this wasn't its first time entering a planetary system. The galaxy has been around long enough for some objects to have had multiple flybys of different stars, each pass altering their speed and direction slightly. These encounters might send a body onto a tighter path toward the galactic centre, or fling it farther into the outer reaches. The gravitational slingshot effect works on the same principle no matter the scale. A small object passing near a large one can trade energy and change course without ever touching it. If 3i Atlas had such encounters in the past, each would have shaped the trajectory that eventually brought it here. The angle at which it entered our solar system tells us that it didn't come from anywhere near the plane where most of our planets orbit. Instead, it approached from a steeper incline, cutting through our system rather than sliding in along a nearly level path. That's another marker of its alien origin. Most comets and asteroids from our own distant reservoirs arrive on paths aligned with the general rotation of our solar system, a lingering echo of the disk of material that formed the planets. Interstellar visitors, by contrast, can arrive from any direction, carrying the momentum of their own histories. Its speed is also telling. By the time it was within our observational reach, it was moving at tens of kilometers per second relative to the Sun. That's far faster than typical comets inbound from our own cloud of icy bodies. The speed doesn't come from any sudden push. It's simply the leftover velocity from its escape from its home star, combined with whatever subtle changes it has accumulated over its long travels. As it fell toward the Sun, our star's gravity added even more to that speed, pulling it into a sharper curve before flinging it outward again. From our point of view, it looked as though it had suddenly appeared on the outskirts of the solar system, already in motion, already aimed on a trajectory that would carry it past the sun once and never again. But if we could zoom out far enough, the picture would show it gliding in from unimaginable distances, the arc of its path bending ever so slightly as it began to feel the pull of our star. That bend is what allowed us to detect it. Had it passed even a little farther away, it might have remained invisible, too faint and too distant for any telescope to notice. Its approach was inevitable once it crossed into the sun's sphere of influence, but nothing about it was guided. There was no target, no aim, just the blind crossing of paths that happens when countless objects drift through the galaxy, each following its own line. The fact that this one's line intersected with ours is as much a matter of chance as it is of physics. Given the size of the galaxy, the rarity of such intersections is staggering, which is why each one feels so significant. During the time it took to travel from the edge of our detection range to the point of closest approach, it would have been bathed in gradually increasing sunlight. The frozen materials in its surface layers, dormant for longer than human memory can grasp, would have begun to warm. For some substances, even a small rise in temperature can be enough to turn solid ice into gas, escaping into space and forming the faint haze of a coma. The path across the stars had been almost unimaginably slow to change until this moment, when for the first time in countless ages, its surface was altered by more than just cosmic rays and micro-impacts. That warming period, brief though it was, may have revealed more about its nature than all the millions of years that came before. As dust or gas escaped, it would have carried with it a chemical record of the object's composition, materials forged in the disk of another star, possibly in a different mix than what we find here. Spectral readings taken during this phase are like looking at a chemical time capsule, one delivered across light years without any deliberate plan. The fact that we were able to take those readings at all is a kind of luck that can't be overstated. After passing its closest point to the sun, the same path that had brought it in began to carry it away. The gravitational assist it received during its swing past the sun ensured that its outbound speed would match or even slightly exceed its inbound speed. Soon, it would cross the same invisible boundary it had entered from, moving once again into the cold, sparse medium between stars. From there, the next part of its path is unknown. It could drift for millions more years before encountering another star. It could be captured briefly by a massive planet in some distant system before being ejected again. Or it might wander without ever approaching another star closely enough to change its course in any noticeable way. Whatever the future holds for it, we know that our role in its story is just a momentary overlap, a brief intersection of paths in a galaxy where most such intersections never happen at all. The path across the stars that brought it here is still ongoing, and our encounter with it is just one stop along the way. When we look at it through our telescopes, we're not just seeing where it is now, we're glimpsing a fragment of a journey that began before our world had the shape we recognise, and that will continue long after our own chapter in the galaxy is over. By the time enough observations had been collected to plot its course with precision, the conclusion was hard to avoid. It wasn't just unusual in speed or in angle of approach, it was outright incompatible with the idea that it belonged to our solar system. The shape of its path told the story as clearly as any label could. Instead of the closed loops we expect from comets and asteroids bound to the sun, it was moving on a hyperbolic trajectory, the kind of curve that doesn't bend back into an orbit but continues outward indefinitely. That curve is the mathematical fingerprint of an object that has come from beyond and will never return. When astronomers measure the orbit of an object, they calculate something called its eccentricity, a number that describes how stretched out the orbit is compared to a perfect circle. For planets, this number is close to 0. For most comets and asteroids, it's somewhere between 0 and 1, with 1 representing a parabolic path, the extreme case of an object falling into the solar system from a great distance and heading back out again. Anything over 1 means it's hyperbolic, moving fast enough to escape the sun's pull entirely. 3i Atlas had an eccentricity well above 1, leaving little doubt about its unbound nature. That wasn't the only clue. Its inbound speed, even before accounting for the sun's gravitational influence, was higher than anything we see from bodies native to our solar system. Comets from our own Oort cloud can arrive fast, but their speed is exactly what you'd expect from something falling inward under the sun's pull. With 3i Atlas, the numbers didn't fit that pattern. Subtract the acceleration caused by the sun, and you're still left with a residual velocity, what astronomers call the excess hyperbolic speed, that can only be explained if the object was already moving quickly before it entered our system. That residual speed is a kind of fingerprint, marking it as an interstellar traveller. Its approach direction also stood out. Most solar system bodies share roughly the same orbital plane, a kind of flattened disk that reflects how the planets and smaller bodies formed from a rotating cloud of gas and dust billions of years ago. Even the comets that come from the distant Oort cloud tend to have paths that relate, however loosely, to that original disk. But 3i Atlas came in on an orbit inclined enough to mark it as an outsider. It wasn't sliding in along the grain of our system, it was cutting across it, carrying the momentum of its own history, rather than conforming to the patterns shaped by our sun. Once these elements were combined, its speed, its trajectory, its angle of approach, there was no reasonable doubt left. The probability that it was a solar system object perturbed into such a path was vanishingly small. That's not to say it's impossible for gravitational encounters within our own system to fling a body outward on a hyperbolic path, but in those cases, the starting point is an inbound path that fits our system structure, not one arriving already out of alignment. The more the numbers were refined, the clearer it became that this was an object whose journey began light years away. The difference between native and interstellar might sound like a technical detail, but it has enormous implications. If it's from here, it's part of a population we already know exists, shaped by processes we've studied for decades. If it's from somewhere else, it's a direct sample of another planetary system's building blocks, preserved in a form we can observe up close. That's why confirming its interstellar status is so important. It tells us that what we're seeing is not just another variation on a familiar theme, but something forged under a different sun. Its composition hints at that difference, though in ways that are subtle. From the spectra gathered during its closest approach, there are signs of the same basic materials we find in comets: water ice, carbon-bearing compounds, dust grains. But the relative proportions may not match what's typical here. The details are still being studied, and in some cases the data is too limited to draw firm conclusions. But even small deviations can be revealing. They suggest that while the chemistry of star system may follow broad similarities, the exact conditions of formation can lead to unique fingerprints. The idea that such an object could arrive here at all is a reminder of how dynamic the galaxy is. Planetary systems are not perfectly sealed containers. During their formation, and even long afterward, they shed material into interstellar space. Giant planets can scatter comets out of their home systems. Close encounters with passing stars can disturb the outer reservoirs of icy bodies, sending some inward and others outward at escape velocity. Over the lifetime of the galaxy, this process has likely sent an unimaginable number of small objects drifting between stars. Most will wander forever in the darkness, but a tiny fraction will by chance pass close enough to another star to be drawn inward. 3i Atlas just happens to be one of the exceedingly rare few that crossed paths with ours while we were watching. It's worth considering how recent our ability to recognise such visitors really is. Before the wide-field survey telescopes of the past few decades, it's likely that many interstellar objects passed through without notice. They would have been too faint and too fast for casual observation. Now, with systems like Atlas and Pan-STARRS scanning the sky every clear night, we can catch these brief appearances. That shift in capability is the reason we can even have this conversation about 3i Atlas. It's not that such visitors have only just begun to arrive, but that we've only just become good enough at spotting them. Even so, each detection is still a matter of timing and luck. The survey systems are thorough, but the sky is vast and the objects themselves are tiny compared to the distances involved. 3i Atlas could have arrived at a slightly different angle or a slightly different time and slipped past us entirely. That's part of what makes these events so compelling. They are rare, they're fleeting, and they remind us that our solar system is not an isolated island, but part of a much larger and more complex traffic pattern in the galaxy. The not from here conclusion isn't just an academic label, it's the foundation for every question that follows. If it's interstellar, then its structure and chemistry are a direct clue to the processes at work in its home system. If it's interstellar, then its journey is a record of millions of years of exposure to the interstellar medium, something we can't replicate with our own local samples. If it's interstellar, then its visit here is part of a chain of events that started in a completely different context and will continue long after it leaves. And so, while the evidence that it's not from here comes from precise measurements of motion and speed, the significance of that fact stretches far beyond the numbers. It places 3i Atlas in a category that is still so small we can count the members on one hand. It makes every image, every spectrum, and every calculation about it more than just another data point. They become part of a growing record of the galaxy's travellers, each carrying a fragment of a distant story. By the time the first telescopes were turned toward it with intent, the mystery had already been set in motion by the measurements of its path and speed. Observers knew they were looking at something that would never come back, something whose visit would be measured not in years but in a scattering of nights and hours. That knowledge gave the moment a weight that didn't need to be spoken. You could feel it in the quiet at the eyepiece, in the way people adjusted their instruments with a little more care, knowing each exposure was part of a sequence we would never have a second chance to repeat. Seen through the instruments that first tracked it, 3i Atlas did not announce itself with fireworks. There was no sweeping tail like the great comets of history, no blazing head that could be seen without optical aid. Instead, it was a point, small, faint, and in most images indistinguishable from the background stars except for its slow drift across the field of view. That motion, captured over the course of minutes or hours, was the first sign that this dot of light was alive, in the sense that it was part of a story, moving not just because of Earth's rotation or the shifting sky, but because it was tracing its own path through space. For many astronomers, the first impression came not from a direct look through an eyepiece, but from the glowing trace on a digital image. Modern telescopes often record light in ways that can be processed and enhanced, making the feint clearer without altering the reality of what's there. The first processed frames showed that this was no mere speck of noise or an artifact in the sensor. It had a steadiness, a consistency of shape and brightness that marked it as something real, a traveller whose light had been patiently making its way toward us for hours before it was finally caught. Those with larger instruments and better conditions began to notice the subtler features. A slight fuzziness surrounded the central point of light, not dramatic, but enough to suggest that dust or gas was escaping from its surface. This was the coma, the thin halo that forms when sunlight heats an icy body enough to release material into space. It wasn't strong enough to produce a visible tail for most observers, but even this faint activity hinted at the processes happening on its surface. For scientists, this was a valuable clue. For those simply looking, it was a reminder that the point of light was more than just a point. It was a world in miniature, reacting to its brief encounter with our sun. One of the striking things about these first close looks was how much interpretation depended on experience. To a casual observer, the object might have looked entirely unremarkable, just another faint smudge among many, but to someone who had spent nights tracking asteroids, comets, and other small bodies, it would have stood out in ways that weren't purely visual. Its movement relative to the star field, its rate of brightness change, even the angle of its path across the sky were all part of a signature that whispered of its unusual nature. Seeing it was not just about the photons hitting your eye or your camera's sensor, It was about reading the story those photons told. The telescopic impressions were also shaped by the conditions under which they were made. From a mountaintop observatory under a dry, steady sky, the object could be captured in long exposures that revealed every faint detail. From more modest setups in less perfect conditions, the challenge was simply keeping it in view long enough to gather useful data. The fact that it was moving relative to the stars meant that standard tracking methods had to be adjusted. Instead of locking onto the stars and letting the object trail across the frame, observers often tracked the object itself, letting the stars blur into short streaks. In the resulting images, the traveller remained sharp and centred, the stationary frame of the cosmos bending around its motion. Some of the earliest high-quality images revealed a slight asymmetry in the coma, as if the material was not escaping evenly in all directions. This could have been the result of jets, localized vents where sunlight reached pockets of more volatile ices, or simply the shape of the body itself. Even without a resolved image of its surface, those asymmetries hinted at a complex and irregular structure. It was not a perfect sphere drifting in the dark, but something shaped by collisions, by the processes of formation, and by the slow erosion of its endless voyage. For the small number of people who did get the chance to view it through a traditional eyepiece, the impression was both less and more than what the images showed. Less, because the human eye is far less sensitive than a camera at collecting faint light, especially at such low brightness. More, because of the immediacy of the experience, the knowledge that you were looking at something that had crossed interstellar space to be here. Even if it appeared as little more than a dim blur, there was something about that direct line from object to eye that made it memorable. The photons entering the retina in that moment had last touched the surface of a world from another star. There's a kind of stillness to observing an object like this. It doesn't perform for us. It doesn't respond to our presence. All the drama is in its history and its trajectory, not in any sudden change we can watch unfold in real time. That makes the act of observing almost meditative. You're not waiting for a burst of activity or a shift in colour. You're simply holding it in your field of view, letting your awareness adjust to the faint details, and knowing that what you're seeing is the only version of this moment that will ever exist. For professionals, those first impressions quickly give way to the work of measurement, determining the precise position, the brightness at different wavelengths, the rate at which the coma is expanding. For others, the memory is more personal, the faint, stubborn presence of a dot that came from nowhere familiar, lingering for a moment in our shared sky before slipping away. Both responses are part of the same encounter, one rooted in data, the other in experience. In either case, the first impressions carry a kind of gravity not because of what the object looks like, but because of what it is. The faint light through a telescope might not be visually spectacular, but it represents something so rare that entire careers might pass without such a sight. That rarity adds a layer of meaning to even the smallest observation. A shift in brightness, a hint of structure in the coma, a curve in the path, each is a note in a score that will never be played again in exactly the same way. As the days passed and more telescopes turned toward it, those first impressions began to merge into a collective portrait. Different observers at different latitudes contributed their own views, filling in gaps, confirming features, and occasionally revealing new details. The object's motion carried it into new starfields, changing the backdrop for each encounter, but never changing the fact that it was the same solitary traveller, seen from countless angles during its short time with us. The first look through a telescope is both the simplest and the most profound part of the encounter. It's the moment when the abstract numbers of an orbital solution become something tangible, when the idea of a visitor from another star is replaced by the reality of seeing it with your own eyes, or at least through your own instruments. It's the quiet recognition that for all the distances it has travelled, it is here now, in our sky, and for a little while we can follow its journey with our gaze. The first close looks didn't just raise curiosity about where it came from, they raised a more immediate and practical question. What exactly were we looking at? Was it best understood as a comet, actively shedding material as sunlight warmed its surface? Was it more like an asteroid, a solid, inert piece of rock that would sail through the inner solar system unchanged? Or did it fall into some category that didn't quite match either of those familiar types? In many ways, these questions were familiar ones. Astronomers have long drawn distinctions between comets and asteroids, but those categories have always had blurred edges. A comet is generally thought of as an icy body, originating from the colder outskirts of a planetary system that produces a visible coma or tail when it approaches a star. An asteroid, by contrast, is usually rocky or metallic, formed in the warmer, denser regions nearer to its star, and doesn't show such activity. Yet we've seen asteroids that sprout temporary dust clouds and comets, whose activity is so minimal they resemble asteroids. The solar system itself contains hybrids and borderline cases. When 3I Atlas was first imaged in detail, there were hints of a diffuse halo around it, the kind of signature we associate with cometary activity. The coma wasn't large or bright, but it was there, just enough to suggest that sunlight was causing some volatile materials to sublimate and escape into space. In that sense, it behaved more like a comet than a rock, but the activity was faint, more restrained than in most freshly inbound comets from our own Oort cloud. That restraint raised questions. Was the surface already depleted of the most easily evaporated ices, perhaps from countless close passes to other stars over its long history? Was it insulated by a layer of dust and crust that slowed the release of gas? Or was it simply composed of materials that don't sublimate as readily? The rotation of the body could also play a role. If it spins in such a way that certain regions receive more sunlight than others, localized activity could be masked when viewed from Earth. Jets or vents might release material only from specific areas, creating an asymmetry in the coma that wasn't immediately obvious in the earliest images. Over time, as the object's orientation changed relative to the Sun, such patterns might shift, revealing more about its surface. Spectral data added another layer to the puzzle. In typical comets, we can detect certain gases, like cyanogen, carbon monoxide, or water vapor, by the way they absorb or emit light at specific wavelengths. For 3I Atlas, the signals were faint and in some cases inconclusive. That's not unusual for such a distant and faint target, but it left the question open. The composition seemed broadly consistent with cometary material, but without the strong, unambiguous emission lines that would clinch the case. It's possible the relevant gases were present but too sparse to register clearly. If it were truly asteroid-like, we'd expect it to remain inert even under increasing solar heating, showing no coma or dust production. That clearly wasn't the case here, which kept the asteroid label from fitting comfortably. But the fact that it didn't erupt into full dramatic activity like some comets do, meant it also didn't fit neatly into the mental image of an interstellar comet shedding vast amounts of material. It was somewhere in between, and that in-between space is often the most interesting place for scientists. Objects like this force us to rethink the categories we rely on. The labels comet and asteroid are convenient, but they're simplifications of a much more complex reality. Planetary systems produce bodies across a spectrum of compositions and structures, and interstellar space is likely populated by just as wide a range. If anything, 3I Atlas was a reminder that our two neat boxes don't necessarily apply to things formed under different conditions, around different stars, in environments we've never directly observed. Some astronomers propose thinking of it primarily as a comet, given the observed activity, but with the caveat that its long journey through the galaxy had almost certainly altered its surface in ways we can't yet fully model. Over millions of years, the constant bombardment of cosmic rays could have transformed its outer layers into a kind of hardened shell, chemically distinct from whatever lies beneath. This shell might act as a partial barrier, keeping most of the internal volatiles locked away until deep cracks or impacts exposed them. In that scenario, the activity we saw would have been just a glimpse of what was still hidden inside. Others suggested that its relatively subdued coma could mean it was a fragment rather than a whole body. perhaps a piece chipped off a larger object during a collision long before it reached our system. A smaller fragment would have a lower mass, possibly allowing it to be more easily ejected from its home system, but also giving it less material to release when heated. The challenge with this idea is that fragments tend to have irregular shapes and rotation rates that can cause significant variation in observed brightness, and while 3i Atlas did show some variability, it wasn't extreme. One of the more intriguing aspects of the discussion was the comparison to the only two other interstellar objects we've studied, Oumuamua and Borisov. Borisov was unmistakably a comet, with strong activity and a well-developed tail. Oumuamua, on the other hand, showed no obvious coma but may have experienced non-gravitational acceleration, possibly due to the release of gases too faint to detect directly. 3i Atlas seemed to fall between these two in behaviour, less active than Borisov but more visibly comet-like than Oumuamua. If we imagine a spectrum with pure rock at one end and a fresh active comet at the other, it might have been somewhere near the middle. The possibility that it could be something outside our usual experience, a type of body not well represented in our own solar system, was always there in the background. If planetary systems formed differently in other regions of the galaxy, they could produce small bodies with unique mixes of ice and rock, or with mineral compositions that alter how they react to sunlight. Detecting such differences requires more detailed data than we can usually gather from a faint, fast-moving target, but even the hint of something unfamiliar is enough to keep the debate alive. As more observations came in during its closest approach, the coma remained modest but persistent. There was no sudden outburst, no dramatic brightening, but also no sign that it was fading prematurely. It maintained its subtle signature, as if to confirm that this was its natural state. For some, that consistency was the most telling detail. It suggested that what we were seeing was not the result of a transient event or a fluke of geometry, but the steady behaviour of a body shaped by its long journey. The reality is that in many cases the line between rock and comet is one of degree rather than kind. A body can be mostly rocky but still contain pockets of ice. It can be mostly ice but heavily coated in dust and debris from past activity. The balance of those materials, combined with the history of heating and cooling, will determine how it behaves when it enters a new star's environment. 3i Atlas, with its faint coma and restrained activity, was a case study in that balance. What made the question so compelling was not just the desire to classify it correctly, but the understanding that the answer could tell us something about where it came from and how it had spent its time between the stars. Was it a survivor of countless close passes to other suns, each one boiling away another layer of ice? Was it a pristine remnant from the outer reaches of its home system, largely untouched until now? Or was it something in between, carrying both the scars of past encounters and the unaltered chemistry of deep space? We may never have a definitive label for it in the simple terms of rock or comet. The more likely truth is that it was both, and that in being both it reflected the messy, varied reality of planetary formation and evolution across the galaxy. The act of deciding which word to use becomes less important than the act of understanding what those words are trying to describe. In the end, whether we called it a comet, an asteroid, or something else entirely, the essential fact remained. It was a small, ancient fragment of another world, passing through ours for the briefest moment, carrying a history written in minerals, ices, and the faint, steady glow it cast back toward us. When sunlight touches an icy surface in the depths of space, the warmth it brings is subtle, but over time it can set in motion a chain of events invisible to the naked eye. For 3 Atlas, as it moved closer to the sun than it had been in countless years, that touch was enough to stir what had been dormant. Beneath the thin, weathered outer layer, patches of ice and volatile material began to turn directly into vapour. That gas pushed outward, carrying with it grains of dust that had been trapped inside since the object first formed. This quiet process is how a coma builds around a cometary body, and even in 3i Atlas's modest case, it told us more than just that it was active. It told us there was a story hidden in the particles it released. dust from such a body isn't like the dust that collects on a bookshelf or drifts in a sunbeam in a room. These grains are fragments of ancient material, unaltered for millions, perhaps billions of years. They're older than our planet, older than the sun itself, having condensed from the gas and dust around another star. In a very real sense, each grain is a tiny sample from a world we've never seen, carried across interstellar space, and offered to us in the most fleeting of ways. When sunlight pushes those particles away from their parent body, they form faint structures, tails, streams and halos that can be detected not by their brightness alone but by the way they scatter light. By analysing that scattered light, astronomers can learn about the size, composition, and even the shape of the grains. Are they smooth or jagged? Are they made mostly of silicates, like tiny bits of rock, or are they coated with organics? Do they cluster in clumps, or drift apart as individual specks? Each of these details offers a clue about the environment in which they formed and the processes they've endured since. For 3I Atlas, the dust it released was faint but persistent. Long exposures under good conditions showed a delicate haze around the central point of light, barely more than a suggestion unless you knew how to look for it. That faintness might seem disappointing compared to the dramatic tales of bright comets, but it was part of what made it valuable. In bright, heavily active comets, the cloud of dust can be so thick that it hides the finer details. Here, the thin release allowed subtle patterns to emerge, gradual changes in brightness that hinted at structure, slight asymmetries that might have been the signature of jets or uneven heating. Studying dust from an interstellar body carries unique challenges. In our own solar system, dust from comets can be sampled directly by spacecraft or observed in detail as it scatters sunlight over time. With an object like 3I Atlas, we have to rely entirely on what can be seen during its brief passage, and that means every night of observation counts. If clouds cover the sky, or if the object moves into a region where it's too close to the sun's glare, the chance to measure certain properties can vanish completely. For this reason, teams around the world coordinated carefully, ensuring that observations were taken from multiple sites to fill in gaps. One of the key things dust can tell us is the ratio of fine particles to larger grains. Fine particles scatter light differently, producing a soft, diffuse glow, while larger grains tend to reflect light more directly, sometimes even producing a slight forward scattering effect that makes the coma appear brighter when the geometry is right. In 3I Atlas's case, the dust appeared to be dominated by smaller particles, which is consistent with the idea that they were recently released from the surface rather than having floated free for long periods. Large grains are harder to accelerate with the gentle push of outgassing, so their absence might indicate a surface that releases material in a more delicate way. Composition is another clue. By passing the light from the coma through spectrographs, astronomers can detect certain features that suggest whether the dust contains carbon-rich compounds, silicates, or other materials. These signatures are faint, but when they can be teased out, they offer a chemical fingerprint of the object's makeup. If those fingerprints differ in significant ways from what we see in our own solar system's comets, it could point to differences in how its parent system formed. So far, the early hints from 3I Atlas's dust didn't scream alien in composition, but subtle differences may still emerge with careful study. There's also the question of how dust behaves once it leaves the body. In our solar system, the interaction between cometary dust and the solar wind, the constant stream of charged particles from the sun, can create complex shapes in tails and halos. For an interstellar visitor, the grains themselves may have slightly different electrical properties due to their long exposure to cosmic rays. This could affect how they respond to the solar wind, potentially creating patterns that differ from the norm. Detecting such patterns is difficult at the faintness level of 3I Atlas, but even small deviations could be revealing. Another factor is the rotation of the object. If it spins, as most do, the release of dust can vary with time. Jets from localized vents will spray particles in specific directions, and as the body turns, those jets sweep across space, creating arcs or spirals in the surrounding haze. Observers watching over multiple nights can sometimes piece together these changes, building a rough model of how the object is oriented and how fast it's rotating. For 3I Atlas, the faintness of the coma made such modelling more difficult, but there were tentative signs that its dust release wasn't perfectly uniform. That asymmetry, subtle as it was, added weight to the idea that we were seeing more than just sunlight heating a smooth, inert surface. Dust studies also connect directly to the broader question of habitability in planetary systems. Many of the ingredients for life as we know it, carbon compounds, water, certain minerals, can be delivered to planets by comets and other small bodies. If the dust from an interstellar visitor contains similar ingredients, it suggests that the raw materials for life may be common throughout the galaxy. If, on the other hand, it's missing some of those key components or contains others we don't see much of here, that could point to environmental differences that might affect the likelihood of a life arising elsewhere. Of course, the difficulty is that by the time we've gathered enough data to begin making such comparisons, the object is already fading into the distance. 3I Atlas was no exception. The dust that whispered its presence was also the dust that marked the countdown to its departure, carried away into space in a stream that would eventually disperse into nothing detectable. For a few short weeks, those grains formed a bridge between our world and its, a link made of sunlight and ancient matter, fragile but real. Some of that dust may still be drifting through the inner solar system even now, following its own new path under the influence of the sun and the planets. In theory, a few particles could even intersect with Earth's orbit at some point in the future, falling into our atmosphere as meteors too small to notice. If that happens, the grains will burn up in a fraction of a second, their long journey ending in a brief flash of heat and light. No one would see it, no instruments would record it, but in a way it would be the final act of 3I Atlas's visit, a silent delivery of matter from another star to our skies. Even without direct capture, the dust it released has already done its work. It's been measured, analysed, and compared to the dust of other comets, both native and interstellar. It's helped refine our understanding of how such bodies behave when they enter a new star's domain. And it's given us one more point of connection to a story that began far beyond our own system, in a place we can only imagine. The whisper of dust is not the kind of signal that makes headlines. It doesn't glow brightly in the sky for millions to see. It doesn't announce itself with drama or spectacle. But for those who know how to listen, it carries a message from the deep past, from the heart of another system, written in the tiniest of grains. And for the brief time it passed near us, that message was there to read, if only in fragments. For all the attention given to its dust, the real heart of the mystery for many scientists came down to a simpler question. How much ice was truly left inside this ancient traveller? Ice is the lifeblood of cometary activity. Without it, the outgassing that drives a coma and tail can't happen. With too much of it exposed, the object can flare dramatically as it approaches a star, sometimes breaking apart entirely. Somewhere between those extremes lies the balance that determines what we actually see from a distance. For an object like 3I Atlas, the question isn't just about whether ice exists, but about where it's hiding, how pure it might be, and how much of it is still capable of reacting to sunlight. If we could somehow slice it open like a fruit, we might see layers telling the story, crusts of hardened dust on the outside, progressively fresher ice beneath, each layer shaped by cycles of heating and cooling across countless eons. But we can't open it. We can only watch how it behaves, infer its structure from the patterns in its light, and guess at the invisible processes happening under its surface. The earliest hints of ice came from that subtle coma we'd already noticed. Even a faint halo of dust usually means gas is escaping to push it outward, and gas means something volatile is turning into vapour. In most comets, that volatile material is water ice mixed with frozen carbon monoxide, carbon dioxide, methane and other compounds. The exact mix depends on the conditions under which the body formed. Bodies that form far from their star tend to have higher concentrations of easily evaporated ices, while those formed closer in lose much of that material early on. What set 3I Atlas apart was the muted nature of its activity. Compared to comets from our own Oort cloud making a first trip into the inner solar system, its release of material was restrained. That restraint could mean that much of its accessible ice had already been depleted, possibly from previous close encounters with other stars. Imagine a similar journey in another system, a pass through the inner region, a flare of activity, a gradual sealing off as dust and crust settle over the vents, then millions of years drifting through interstellar space, exposed to cosmic rays and micrometeorite impacts that further alter the outer layers. By the time it reaches us, the only ice that can still sublimate might be buried deep beneath a weathered shell. This hardened shell, often called a mantle, could be just centimetres thick in some places, metres in others. In certain comets, the mantle forms quickly, in just a few passes near a star, when dust left behind by escaping gas settles back down to insulate the surface. In others, it builds slowly, layer by layer, over much longer timescales. A mantle makes it harder for heat to penetrate deeply enough to trigger strong outgassing. It also changes the way the object reacts to sunlight. Instead of a steady boil of gas, you might get occasional bursts when a crack opens, releasing a pocket of pressurized vapor all at once. For 3I Atlas, there were no dramatic bursts recorded, at least not from what could be seen from Earth, so it's likely the heating was gentle enough, or the ice buried deep enough to prevent such events. The lack of sudden flares didn't mean the ice wasn't there. In fact, the persistence of its activity over weeks suggested a steady supply, possibly from a few active areas where the mantle was thinner or where fractures allowed gas to escape slowly. Spectroscopy offered the best hope of identifying the exact kinds of ice present. Certain molecules give off distinct signatures in infrared or ultraviolet light, and detecting them can confirm their presence even when they're invisible to the eye. In bright comets, water vapor emissions can be detected easily, along with traces of carbon monoxide or carbon dioxide. For 3I Atlas, the signals were faint, some barely above the noise, but there were tantalizing hints of water and perhaps carbon-bearing gases. The difficulty is that such weak detections can be ambiguous, and without more time or better positioning, confirmation can remain just out of reach. The question of ice also connects directly to the object's possible origin. In our solar system, the proportion and type of ice in a comet can tell us whether it formed near the giant planets or far out in the cold edge of the protoplanetary disk. For an interstellar object, that same information could offer a clue about the architecture of its home system. If it contains high amounts of volatile ices like carbon monoxide, it might have formed in a region even colder than our own Kuiper belt. If it's dominated by water ice with fewer volatiles, it might have formed closer in a zone where water could freeze but lighter compounds couldn't remain stable. Some researchers suggested that the balance of ice and dust in 3I Atlas might actually place it closer to Oumuamua than to Borisov in terms of activity, even though its visible coma made it more obviously comet-like. In other words, it could be that what we were seeing was the last whisper of activity from a body that had once been far more reactive. If so, then catching it now was like catching the tail end of a long performance, when the stage lights are dimming and the sound is fading, but the core of the song is still there to hear if you listen closely. The survival of ice across such long interstellar journeys raises interesting physical questions. Space between the stars is cold, only a few degrees above absolute zero, so you might think ice would remain perfectly preserved. But temperature isn't the only factor. Cosmic rays can penetrate surfaces, breaking molecular bonds and transforming ice into more complex, less volatile compounds. Over millions of years, this slow radiation processing can turn bright, clean ice into dark, organic, rich crusts. Once that happens, the ice beneath is protected from sunlight, but also hidden from direct interaction with the environment until something disturbs the surface. A disturbance could come from many sources: an impact with a small meteoroid, a stress fracture caused by rotation, or simply the uneven heating that occurs as the object's orbit takes it closer to a star. In some comets, we've seen whole patches of surface collapse, exposing fresh ice and triggering sudden outbursts of gas and dust. With 3 Atlas, if such events happened at all, they were small enough or brief enough to escape detection during its pass. That absence of violent changes may tell us as much about the ice as a dramatic flare would have. It may mean that its structure is relatively stable, its remaining ice distributed in a way that doesn't invite sudden collapse. One of the more intriguing possibilities is that some of its ice could be of a type rare in our solar system. While water ice is common here, other forms like exotic hydrates or nitrogen ice are less so, and their behaviour near the Sun can be quite different. Detecting them requires very specific observations, often in parts of the spectrum not accessible to ground-based telescopes. In theory, an object like 3I Atlas could bring with it ices that formed under chemical conditions unique to its home star's environment, ices that might never naturally occur here. Even the faintest evidence of such material would be a significant discovery. The truth is that we'll never know the full inventory of its interior ices unless a spacecraft someday manages to intercept an interstellar visitor and study it up close. Until then, we work with the clues we have: the shape and brightness of the coma, the presence or absence of certain emission lines, the persistence of activity as it moves away from the Sun. From those clues, we build the most likely picture: that somewhere beneath its ancient crust, shielded from countless years of cosmic radiation, patches of ice still endure, waiting for the rare moment when a star's warmth brings them back into motion. For 3 Atlas, this encounter was that moment, and for us, it was a chance to catch the brief shimmer of vapour and dust that betrayed the presence of something that had been sleeping for far longer than human history can measure. The question of ice isn't just about whether it's there, it's about what it can tell us about where this traveller came from, what it has been through, and how much of its original self it still carries after crossing the vast cold gulf between the stars. When we speak of a time capsule on Earth, we usually mean something placed deliberately in the ground or sealed in a building's walls. A small container meant to be opened decades later, revealing a frozen moment in history. With 3I Atlas, the idea is similar, but the scale and the time involved are almost beyond comprehension. It is a time capsule not of human history, but of the very earliest moments of a planetary system that is not our own. It carries within it the physical record of conditions that existed around another star, perhaps billions of years ago, preserved in a form we can still detect today. Every grain of dust, every trapped bubble of ice, every mineral on its surface is a page in that record. They were shaped before Earth formed, before our Sun ignited, in a protoplanetary disk of gas and dust that has long since dispersed into the galaxy. The forces that brought those materials together, gravity, temperature gradients, collisions, are universal, but the exact recipe varies from star to star. The result is that bodies like 3I Atlas can carry subtle but telling differences from anything we've ever studied up close. The fact that it survived at all to reach us says something about its structure. Interstellar space is not entirely empty, and over millions of years, collisions with tiny particles and exposure to cosmic radiation can slowly erode and alter a small body. Some may be worn down to fragments too small to detect, others may shatter during close passes to stars. The ones that survive are the tough ones, those that found themselves on paths avoiding catastrophic encounters, able to endure long stretches of cold and darkness. 3 Atlas, by the time it arrived here, had already proven itself a survivor many times over. Its surface, likely darkened by radiation over eons, would have been a kind of armour, sealing in the more pristine material beneath. If we could look past that weathered exterior, We might find layers showing the gradual accumulation of dust and ice during its formation, the chemical imprints of its home star's radiation, and the occasional disruptions from impacts. That layering, if preserved, would be like geological strata on Earth, each one telling a part of the story of its environment. Unlike Earth's rocks, though, these layers would have remained undisturbed for vast stretches of time, unaffected by wind, water, or tectonic shifts. In that sense, the object is not just a time capsule of its own system's early history. It's a kind of controlled experiment in planetary science, one where the variables have been frozen for almost the entire lifespan of the galaxy's current era. Studying it, even from afar, allows us to test our theories of how small bodies form, evolve, and interact with their surroundings. The faint dust it released, the gases it vented, and the light it reflected are all parts of that experiment's readout. What makes it even more compelling is that it's not just any sample from its system of origin, it's a sample selected by the physics of ejection. To be thrown out of a planetary system entirely, a small body usually needs a powerful gravitational interaction. In our solar system, giant planets like Jupiter can fling comets out into interstellar space after a close pass, giving them the speed to escape the sun's gravity forever. The same must happen in other systems. That means 3i Atlas may have passed near one or more massive planets in its own home before being launched into the dark. Those encounters could have altered its surface, cracked it, or even stripped away part of its outer layers. In this way, its ejection is part of its history, as significant as its formation. The travel time between its ejection and its arrival here is impossible to know precisely without a clear origin point, but it could easily span tens or hundreds of millions of years. Over that timescale, a body like this becomes more than just a leftover from planet formation. It becomes a record of what survives the long voyage. If some ices are still present, as the coma suggests, they have endured longer than many would have thought possible. If organic molecules are still intact, they have travelled through some of the harshest conditions in the universe without being destroyed. Those possibilities feed into one of the most profound reasons scientists are eager to study interstellar objects, the question of whether the building blocks of life are common and mobile in the galaxy. If 3i Atlas contains amino acids, complex organics, or other prebiotic materials, then it's a piece of evidence that such chemistry may be widespread, able to move between star systems. We already know from meteorites and comets in our own system that such compounds can form naturally, but finding them in material from another star would be a direct link between planetary systems. It would mean that the seeds of life are not confined to their birthplaces, but can drift across the galaxy, waiting for the right conditions to take root. Even without direct sampling, we can begin to look for hints of such materials through spectroscopy. Certain organic compounds leave faint but recognizable marks in the way an object reflects and emits light. For 3i Atlas, the faintness of the signal made such detection difficult, but that didn't stop researchers from trying. Every observation, every set of measurements taken during its brief pass was another attempt to unlock part of the capsule's contents without opening it. The challenges like trying to read a letter sealed in a bottle, using only the shape of the glass and the way it glints in the sun to guess what's inside. Of course, the most dramatic way to learn from a time capsule like this would be to send a spacecraft to intercept it. In theory, that would allow us to directly analyse its dust, ice, and rock, to drill beneath the surface and see the untouched material within. The reality is that our current technology makes such missions difficult to launch on short notice, especially when the target is discovered only months before its closest approach. But the dream of catching one is alive in the minds of many planetary scientists. The idea is that if we can predict the path of an interstellar visitor far enough in advance, we might someday have a spacecraft ready to meet it, turning a fleeting observation into a detailed exploration. Until then, we rely on the tools we have from Earth and near-Earth space. Each observation of 3i Atlas adds a fragment to the picture. The way its coma changes with distance from the sun, the subtle colour shifts that may hint at its composition, the rate at which its brightness fades. None of these alone tells the whole story, but together they begin to outline the shape of what's inside the capsule. We may not be able to read the entire message, but we can catch enough words to understand its significance. The most striking thing is that everything we learn from 3i Atlas also prepares us for the next visitor. Each time we refine our ability to measure, compare, and interpret these fleeting objects, we increase our chances of recognizing a particularly important one early enough to study it in more detail. In that way, every time capsule we encounter, even briefly, becomes part of a larger archive, one that's building slowly with each pass of an interstellar traveller. The true richness of 3i Atlas lies not just in what it contains, but in the fact that it made it here at all. Somewhere in another part of the galaxy, a star once shone down on the cloud of gas and dust that gave birth to it. Somewhere in that system, giant planets stirred the smaller bodies, sending some inward to their star and others outward into the void. One of those outward-bound bodies, against all odds, crossed paths with our sun, and for a short time we could see it, measure it, and wonder about the story it carried. That's what makes calling it a time capsule feel so apt. It is both a relic of the past and a messenger to the present, bringing with it the possibility that we are not just passive observers of our galaxy's history, but participants in a shared exchange of material that spans the distances between stars. Whenever an interstellar object is found, it doesn't take long for the question to surface. Could it be something made, not born? It's an idea that sits quietly in the background of almost every discussion, even when most scientists know that the odds are overwhelmingly in favour of a natural origin. Still, the possibility, however remote, is not dismissed out of hand. It's part of the scientific process to at least ask whether what we're seeing could have an artificial explanation before settling on the natural one. With 3i Atlas, that question lingered just as it had with Oumuamua before it. The idea of alien engineering brings with it a specific set of expectations. We might imagine perfectly smooth surfaces, clean geometric shapes, unusual materials, or deliberate non-random motions. A truly engineered object might behave in ways that defy our understanding of natural physics, or at least stretch it in a direction we've never observed before. In practice, though, the boundary between what is unexpected and what is impossible can be very fuzzy. Natural bodies can have odd shapes, strange rotations, and unusual chemical signatures without any intervention from intelligent builders. The galaxy's processes are creative enough without help. When Oumuamua was discovered, its elongated shape and unusual acceleration sparked a burst of speculation about alien technology. Some wondered if it could be a fragment of a larger structure, or even a thin sail designed to move with the pressure of starlight. In the case of 3i Atlas, the early data didn't provide quite the same visual mystery. It behaved in a more comet-like way, with a coma and a hint of dust emission that suggested a conventional, if faint, release of gas. But even that wasn't enough to entirely close the door on less conventional explanations. One of the main reasons the idea remained in play is that alien engineering doesn't have to mean something functional in the way we design a spacecraft. It could mean debris from a civilization's construction efforts, fragments of structures long abandoned, or relics of machines no longer in use. Over cosmic timescales, anything built would eventually degrade, break apart, and weather under the same conditions that affect natural bodies. A piece of alien technology drifting for millions of years between the stars might end up looking very much like an oddly shaped rock or ice fragment by the time we see it. For scientists considering the possibility, the test becomes one of finding features that are extremely difficult to explain without intelligent design. These could include precise symmetry, exact repeating patterns in rotation or light reflection, or spectral signatures indicating the presence of alloys or composites not produced by natural processes. With 3i Atlas, none of these clear indicators emerge from the observations. Its rotation seemed irregular in a way consistent with natural bodies, and its spectrum matched what might be expected from a mixture of dust, ice, and organic rich surface material. That said, the data we have is limited by the object's faintness and its brief time in our skies. The absence of evidence is not evidence of absence. It simply means that with the tools and time we had, nothing clearly artificial was detected. The limitations of observation always leave room for the unknown. We may never know if something more unusual could have been revealed by a closer look, because the opportunity to take that closer look is already gone. This is why the conversation about alien engineering often becomes less about proof and more about possibility. A comet-like object from another star is already rare enough to make us reconsider what's out there. The fact that it is physically possible for technology to survive long interstellar journeys, whether drifting aimlessly or still functional, means that the hypothesis, however unlikely, is worth keeping somewhere on the table, not as the first explanation, but as one that should be tested if the data ever points that way. It's also worth remembering that engineered could mean something less mechanical and more biological, at least in concept. There are speculative ideas in which life itself might design and release objects for seeding other systems. Probes carrying microorganisms designed to survive the journey and awaken when warmed by a new star. Such ideas fall into the realm of Panspermia theory, and while they remain unproven, they are intriguing enough that they surface in discussions about interstellar visitors. If 3i Atlas had carried such a payload, it would likely be impossible to detect from afar, but the thought of such a delivery system reminds us that engineering isn't always about machines. It can be about purpose. The difficulty, of course, is that our default expectation must remain that objects like this are natural. The simplest explanation that fits the data is generally the one to start with, and for 3i Atlas that explanation is that it is a fragment of ice and rock shaped by its home system and by its long journey through space. Yet the act of even entertaining the engineered possibility has value. It sharpens our tools, forcing us to define exactly what evidence would be needed to support such a claim. It also keeps our thinking flexible, reminding us that nature's range of possibilities is vast, and that our current catalogue of known shapes, colours and behaviours is far from complete. It's in that spirit that some researchers quietly compared its measurements to models of thin, sail-like structures or hollow shells, not because they believed that's what it was, but to see if anything in the data might fit better with those models than with a natural comet. So far, the match was always closer to natural behaviour, but even those comparisons will help if we ever find something that does deviate in a more striking way. The groundwork being laid now could someday allow us to recognise an engineered object when it appears, if it ever does. For now, the story of 3i Atlas in this context is one of restraint. It gave us just enough to keep the door to speculation open, without ever offering the kind of anomaly that would push that speculation towards serious reconsideration. We learned what an interstellar object with modest, comet-like activity looks like under close watch, and in doing so, we also learned more about what signs to look for if we ever want to distinguish the natural from the constructed in a meaningful way. What remains is the awareness that even if it wasn't engineered, it has still been shaped by collisions, by heat, by cold, by the slow turning of the galaxy itself. Whether those shaping forces were entirely natural or once guided by hands, we'll never see, is a question we can't answer for this visitor. But the very act of looking for an answer is part of why its visit mattered. Visit. It reminded us to keep our definitions loose enough to hold the unexpected, and to never assume that what passes through our sky is entirely familiar. One of the simplest questions we can ask about an object in space is also one of the most difficult to answer from a distance. What shape is it? It sounds like the sort of thing that could be resolved with a few good images, but for faint distant bodies like 3i Atlas, direct pictures revealing its outline aren't possible with our current telescopes. Instead, we have to infer its shape indirectly, mostly by watching how its brightness changes over time as it rotates. Every irregular body in space spins, and as it does, the amount of sunlight it reflects toward us changes depending on which side is facing Earth. This creates what astronomers call a light curve, a graph of brightness over time. The more elongated or irregular the object, the more dramatic those changes in brightness tend to be. By studying the light curve carefully, scientists can estimate the object's overall proportions, its rotation period, and sometimes even clues about whether it's tumbling chaotically rather than spinning smoothly. With 3i Atlas, the light curve was subtle. It didn't show the kind of extreme fluctuations that suggested a long needle-like form, nor did it appear perfectly stable in a way that might indicate a near-spherical body. The changes in brightness were moderate, suggesting something neither highly elongated nor completely symmetrical. In some ways, this made it more challenging to interpret, because moderate variations could come from many possible shapes. A slightly stretched sphere, a lumpy potato-like form, or even a roughly rounded body with one prominent protrusion. The fact that it displayed a faint coma complicated things further. A coma acts like a veil, softening the brightness changes caused by rotation. When sunlight scatters off both the surface of the body and the dust around it, the result is a blended signal. This means the actual variations in brightness from rotation alone could have been stronger than what we measured, hidden beneath the steady glow of escaping material. Correcting for that effect requires careful modelling and assumptions about how much of the light is coming from the coma versus the nucleus. Some astronomers attempted those corrections and came away with an estimate that the object's length could be anywhere from 1.5 to 3 times its width. That's a broad range, and the uncertainty reflects the difficulty of making precise shape determinations from light curves alone. The range still allows for a variety of interpretations. Perhaps it's a squat ellipsoid, perhaps a chunk of a once larger body broken in a collision, perhaps something closer to a flattened disk. The exact answer is locked away in data we can't yet collect. Rotation rate offers its own set of clues. Bodies that spin too quickly can't hold themselves together unless they're solid rock or metal. Icy, loosely bound bodies, often called rubble piles, tend to rotate more slowly because a fast spin would tear them apart. For 3i Atlas, the rotation appeared to be on the slower side, which might hint at a less cohesive interior, possibly a mix of ice and rock held together by gravity and intermixed grains. That would fit with its faint cometary activity, and the idea that it still harbours volatile materials beneath its crust. Another intriguing possibility is that it might be in a state of non-principal axis rotation, what's sometimes called tumbling. In this state, the object isn't spinning smoothly around a single axis, but instead wobbles, with different parts of it turning toward the sun at different times. Tumbling can happen after a collision or a strong gravitational encounter, both of which might have been part of its history before leaving its home system. Detecting tumbling requires light curve patterns that repeat in complex ways, and for 3i Atlas, the faintness of the signal made it hard to confirm. But there were hints that its rotation might not be entirely steady, which would add to the picture of it as a battered fragment shaped by a long and eventful past. When people speculate about alien engineering, shape often comes up as a key point of interest. A perfectly flat disk, a long thin rod, or a geometrically precise polyhedron would be difficult to explain naturally. But here, nothing about 3i Atlas's inferred proportions pushed it into that territory. Its likely form was irregular, not symmetrical, and consistent with the kinds of shapes we've seen in many small bodies both in the asteroid belt and among comets. In other words, it didn't wave any red flags from the perspective of shape alone. Even so, shape still matters for understanding its evolution. The amount of surface area exposed to sunlight, the way that sunlight is distributed across its surface during rotation, and the potential for certain regions to experience repeated heating all affect how it loses material over time. If one end of the body has a darker, more heat-absorbing surface, it could warm enough to vent gas while the other end remains dormant. Over millions of years, that uneven activity could gradually change the shape itself, sculpting pits, ridges, and depressions. There's also the question of whether its shape now is the same as it was when it left its home system. Collisions during the ejection process could have chipped away parts of it, leaving jagged edges, Micrometeorite impacts during its long drift could have smoothed some surfaces, while leaving others cratered. Sublimation of ice near the surface might have caused sections to collapse inward, changing the silhouette. In that sense, what we're seeing is not just the shape of a single moment, but the accumulated record of many moments over unimaginable spans of time. While it's tempting to think of shape as a fixed property, in space it is often dynamic. Small bodies can slowly change form under the influence of the Yorp effect, where sunlight itself, absorbed and re-emitted as heat, exerts a tiny torque that can alter their spin over millions of years. A change in spin rate can, in turn, redistribute material on the surface, or even cause parts of the body to break away. If the 3i Atlas has been subjected to this kind of subtle shaping for millions of years, then its current proportions may be the result of a balance between those forces and the stabilizing effect of its own gravity. One of the more human aspects of studying an object's shape is that our brains are wired to see patterns and familiar forms. Give us a faint, noisy signal, and we might imagine a ship-like outline, a spear, a coin. But science demands that we strip away those impressions and focus on what the data truly supports. For 3i Atlas, the disciplined answer is that it is likely irregular, possibly elongated, but not dramatically so, and its rotation is slow enough to suggest a body that is at least partly porous rather than solid throughout. Beyond that, the rest is imagination. Fun to entertain, but not confirmed. Still, there's value in imagining, because it keeps our minds open to possibilities and drives the questions we ask in future observations. If we ever see another object with similar proportions but unusual behaviour, strange accelerations, unexpected light patterns, we'll be better prepared to notice and interpret it. In that sense, even a shape as ordinary as that of 3i Atlas contributes to a growing database of what normal looks like for interstellar visitors. The more we know about normal, the easier it will be to recognise extraordinary. Shape is more than just a geometric property. It's a clue to history, composition, and fate. For 3i Atlas, whatever its exact silhouette, that outline has been carried across uncountable distances through countless encounters and has now been briefly recorded in our own archives. The line it draws in space may be rough and uneven, but it's a line that began under another sun and for a moment crossed our own. Whenever a new interstellar object enters our skies, there's a natural temptation to listen as well as to look. Shape and light can tell us about size, spin, and composition, but the space between the stars is not limited to silent messengers. Some scientists and even more enthusiasts are always ready to ask if such a visitor might be sending something, intentionally or not, that our instruments could detect. That question, for all its romance, is not idle curiosity. It's grounded in the idea that if an alien civilization exists and has ever chosen to explore or to communicate, the debris and tools it sends might, just might, announce themselves in ways we could pick up. With 3i Atlas, that meant paying attention not only to the light it reflected, but to any energy it might emit beyond what we'd expect from a natural body. The most obvious place to start is radio. Radio astronomy has a long history of revealing signals that our eyes cannot see. Pulsars, distant galaxies, the faint afterglow of the Big Bang itself. A body like 3i Atlas, if it contained or carried any kind of transmitter, might conceivably be broadcasting at a wavelength detectable to us. Even if it wasn't transmitting deliberately, there's the possibility of picking up non-natural emissions from exotic materials interacting with the solar wind or with sunlight. The first step in such listening is to define what non-natural means in this context. Nature produces a vast range of radio noise, lightning storms on planets, the magnetic fields of giant worlds interacting with charged particles, the background hiss of the universe itself. To stand out from all that, a signal would usually need to be narrow in frequency, structured or repetitive in a way that is unlikely to happen by chance. Narrowband signals are especially interesting because they don't tend to occur in nature over long durations. A spike at a very precise frequency that repeats in a predictable way is immediately worth a closer look. As soon as 3i Atlas was confirmed to be interstellar, a few observatories devoted time to listening for exactly that kind of signal. These sessions were often short, squeezed in between other scheduled work, because the object's faintness made it a challenging target. The signal-to-noise ratio was always going to be low, especially given that the object was surrounded by a diffuse coma whose gases might scatter or absorb any emission. Despite those challenges, the data was collected and sifted through by algorithms designed to search for patterns. The result? Nothing that stood apart from the ordinary hiss and pop of cosmic radio noise. That doesn't mean there was nothing there. It just means that if there was, it was too faint, too brief, or at a frequency we weren't monitoring to be detected. There's also the reality that any truly alien technology might use modes of communication entirely outside our current detection capabilities. Radio is attractive to us because it's efficient over long distances and easy to generate, but that doesn't make it universal. Civilizations more advanced than ours might communicate with methods we haven't even conceived of yet, or in forms so subtle they'd be invisible against the backdrop of natural phenomena. Radio wasn't the only range of the spectrum checked. Optical searches, though more difficult to coordinate, were also attempted. The idea here is that a flashing light or laser signal could, in principle, be aimed in our direction. Such signals could be extraordinarily bright in a narrow beam while being undetectable outside it, which means that even if they existed, they might be missed entirely unless we were in the right spot at the right time. For 3i Atlas, the observational campaign didn't turn up any optical pulses that looked artificial, but again, the limitations of time, sensitivity, and geometry keep us from calling that a definitive absence. Then there's the matter of more indirect emissions, things like unusual thermal signatures or magnetic fields that don't match what we'd expect from an inert, naturally formed object. If, for example, some part of its surface warmed in a pattern inconsistent with sunlight alone that could hint at internal processes. Sensitive infrared telescopes can look for this kind of heat pattern, though faint and distant objects like 3i Atlas make such observations tricky. In this case, the measurements were consistent with reflected sunlight and the low-level warming expected from gas release. There was no clear anomaly in the thermal data. Magnetic field measurements are even more difficult, especially at great distances. A strong, organised magnetic field could be a natural result of certain mineral compositions, but it could also arise from current-carrying structures, wires, coils, or other conductive shapes. Unfortunately, detecting such a field from a small object halfway across the solar system is beyond our current reach without a probe nearby. As a result, the possibility remains purely hypothetical. The absence of clear signals doesn't lessen the importance of listening. In fact, every non-detection is itself a data point. It tells us something about the limits of what we might expect to detect from a body like this, and it helps refine the search for the next time. The more we understand about the natural radio and optical noise from interstellar visitors, the easier it becomes to pick out genuine anomalies when they appear. In that way, even silence is useful. Silence also serves as a reminder of scale. If there was ever anything artificial about 3i Atlas, it might be so old and so far gone from its original purpose that no trace of its makers remains in a form we can detect. A spacecraft left adrift for millions of years would eventually lose power unless equipped with a self-sustaining energy source. Surfaces would erode under constant micrometeorite bombardment, and coatings would break down under cosmic radiation. Over time, it could become indistinguishable from any other chunk of rock and ice. In a sense, that's the ultimate camouflage, not deliberate concealment, but the natural weathering of the galaxy. Listening for signals is as much about philosophy as it is about physics. It's an acknowledgement that while the odds of intercepting a deliberate message are small, the potential reward is so great that it's worth the effort. It's a patient kind of science, one that accepts that most nights will yield nothing but background static, but also that every so often something unexpected could emerge from that static. The history of astronomy is full of discoveries made by those willing to listen to the faintest whispers in the noise. In the case of 3i Atlas, the whispers we heard were all natural. The hiss of its motion through space, the subtle scatter of sunlight in its dust, the faint heat from its slowly turning surface. If there was anything more, it stayed hidden, perhaps by distance, perhaps by time, perhaps because there was nothing to reveal. Yet the act of listening was never wasted. It became part of the broader observation, part of the archive that will be compared against the records of future visitors. And if one of those visitors does carry something more than dust and ice, we'll be better prepared to recognize it when it arrives. Every encounter with an interstellar visitor is precious, partly because they arrive so rarely, but also because each one gives us a slightly different lens through which to see the galaxy. The few we've recorded so far, Oumuamua, Borisov, and now 3i Atlas, are so different from one another that it's difficult to imagine them coming from the same kind of environment, and perhaps they didn't. Instead, they might represent different outcomes of the same grand processes that unfold around young stars, processes we've only begun to understand by studying our own solar system. When Oumuamua swept through in 2017, it was a shock in more ways than one. It was the first confirmed interstellar object we'd ever seen, and it didn't fit neatly into any category we had. No coma was visible, no tail of dust or gas. Its path through space showed a tiny acceleration that couldn't be explained purely by gravity. Its brightness varied dramatically as it rotated, suggesting an elongated shape, unlike anything we'd previously observed in our solar system. And its surface appeared unusually reflective for an object of its size and presumed composition. Those details opened the door to a wide range of interpretations, from an icy shard with a crust of organic rich material to a sliver-like fragment pushed slightly, by outgassing invisible to our instruments, and even to speculative ideas about artificial origins. 2 years later, Borisov arrived, and in almost every respect it was different. It looked and behaved like a comet from our own solar system, but brighter and more active than many of the long-period comets we've studied. It had a large coma, a clearly visible tail, and a composition that included water ice and carbon-based molecules. In some ways, it was reassuring. It proved that interstellar space could carry the same kind of icy wanderers we were used to, and that our detection methods could catch them if they came close enough. But Borisov's brightness and activity also hinted that it was relatively fresh. Its ice is well preserved, perhaps having spent most of its life far from the heat of any star before arriving here. Now, with 3i Atlas, we find something in between. It shows a coma and some dust, but far less than Borisov. Its activity is modest, more restrained, suggesting that some of its volatiles may already have been depleted or buried deep beneath a mantle. Its shape and brightness variations are less extreme than Oumuamua's, but its behaviour still sets it apart from most comets we've observed in our solar system. In a sense, it's a reminder that there's no single template for an interstellar object. Each one we've seen so far has been its own distinct case, shaped by the specific history of its birth, ejection, and long journey through the void. Looking at them together, patterns start to emerge, though they're faint and tentative. Oumuamua, with no visible coma, might represent a body whose surface had been sealed and hardened long before entering our solar system, with its volatile materials either exhausted or locked away beneath an insulating crust. Borisov, with its intense activity, might have been almost untouched since its formation, carrying a near-pristine load of ice that erupted when it approached our sun. 3 Atlas, somewhere in between, could be a body that has lost some but not all of its accessible volatiles, its activity subdued but still present. From these differences, we can start to think about what kinds of environments might produce such variety. Bodies like Borisov could form far from their star, in regions cold enough to preserve the most volatile ices. Objects like Oumuamua might come from warmer zones, or might have been altered by repeated passes near their star before being ejected, Something like 3i Atlas could represent a middle path, formed in a relatively cold region, but exposed at some point to heating or other processes that reduced its store of ice without erasing it entirely. Ejection mechanisms also play a role in shaping what we see. A close encounter with a giant planet can fling an object into interstellar space, but such an encounter might also crack or fragment it, alter its spin, or strip away loosely bound material. An object ejected after passing close to its star might carry a baked, hardened surface. One sent out from a distant, cold region might retain more of its ices. Over millions of years of travel, additional forces, micrometeorite impacts, cosmic ray exposure, thermal cycling, further sculpt what remains. By the time we see these objects, their current state is the sum of all those influences. The lessons from past visitors also include the sobering reminder that our ability to study them is limited by time. Each one spends only a short period within reach of our most powerful instruments. With Oumuamua, it was already on its way out of the inner solar system by the time it was identified, giving us only a few weeks of good observation. Borisov offered more time but still moved quickly, fading as it retreated into the outer reaches. 3i Atlas followed the same pattern: discovered, observed for a brief season, then gone. That urgency shapes the way astronomers respond, forcing rapid coordination between observatories and quick decisions about which measurements to prioritize. Another important takeaway is how detection itself is changing. Before Oumuamua, most surveys weren't designed with interstellar objects in mind. Their discovery was a surprise, but it also demonstrated that our telescopes were just sensitive enough to catch such visitors if we happened to be looking in the right direction at the right time. Borisov's detection showed that with slightly improved coverage and data analysis, we could find them earlier and track them longer. With 3i Atlas, detection came early enough to begin serious observation before it reached perihelion, the closest point to the Sun. This trend suggests that as survey technology continues to advance, we might start to spot interstellar objects not just weeks or months, but years before they arrive, a change that could make all the difference for deeper study. We've also learned from past visitors that public interest can be a powerful ally. Oumuamua captured imaginations in a way few astronomical discoveries do, drawing attention to the concept of interstellar travel, both natural and engineered. That attention helped secure telescope time and funding for follow-up observations, even if only for a short while. Borisov, while less sensational in the headlines, still benefited from that heightened awareness, as did 3i Atlas. The more the public understands about these objects, the easier it becomes to mobilize resources quickly when the next one appears. Perhaps the most valuable lesson is that diversity is the rule, not the exception. If we'd only seen Oumuamua, we might have thought that interstellar objects were all inert, crusted fragments with no visible activity. If Borisov had been the only example, we might have concluded they were all comet-like and rich in volatiles. 3i Atlas shows us that the truth is far more varied, and that each new arrival is likely to surprise us in some way. That understanding changes how we plan for the future. Instead of designing observation strategies around a single expected type, astronomers are preparing for a wide range of possibilities. This variety also hints at something deeper, that planetary systems everywhere may be constantly exchanging material. Each of these visitors was once part of another star's retinue, shaped by its local environment, then cast out to wander. Some may pass through several systems in their lifetime. A few might even collide with planets, delivering new materials, perhaps even complex organics, across the gulf of space. The idea that our solar system might receive such gifts, and that we in turn might send our own fragments out into the galaxy, is a reminder that the exchange of matter is a quiet but constant part of the Milky Way story. And so, when we look back on these past visitors, we see more than just isolated curiosities. We see pieces of a larger puzzle forming, a puzzle that tells us about the building blocks of planets, the processes that shape small bodies, and the potential for life's ingredients to travel between worlds. We see opportunities missed because we weren't ready, and opportunities taken because we've learned from those misses. Most of all, we see the importance of being prepared, because somewhere out there, another one is already on its way, carrying its own lessons for those ready to listen. When scientists think about what these interstellar travellers might carry, they don't just stop at ice and dust. There's a bigger question that naturally follows once you consider that these objects are fragments of other worlds. Could they transport the ingredients, or even the precursors of life from one planetary system to another? It's an idea that has been around for a long time, wrapped into the concept of Panspermia, the possibility that life, or the chemistry that can lead to life, might spread through space aboard natural vehicles like comets, asteroids, or ejected planetary debris. The first step in thinking about that is to ask whether the materials needed for life can even survive in space for the kinds of timescales we're talking about. We know that organic molecules, the building blocks of proteins, nucleic acids, and many other vital components of living systems, can form naturally in a wide range of environments. They've been detected in meteorites that have fallen to Earth, in comets within our solar system, and in the thick clouds of gas and dust that give birth to stars and planets. Some of these molecules are surprisingly resilient. They can endure ultraviolet radiation, cosmic rays, and the cold vacuum for long periods, especially if they're shielded by rock or ice. If 3I Atlas contains such molecules, it wouldn't be unique in that respect. Many comets in our solar system harbour complex organics. What would make it special is that those molecules would have formed under conditions that could be very different from the ones in our own solar system. They might carry subtle chemical fingerprints of a different mix of elements, different patterns of heating and cooling, or even different forms of the same basic compounds. To a chemist, these differences would be like finding a new dialect of a familiar language, still recognisable, but with its own character. The next question is whether something more than chemistry could make the journey. Could actual microorganisms frozen deep inside an object like 3I Atlas survive the eons between star systems? On Earth, some microbes are astonishingly tough. They can survive extremes of temperature, dryness, radiation and pressure that would destroy most forms of life. Some can enter a dormant state, essentially shutting down their metabolism until conditions improve. Experiments have shown that certain bacteria can endure years in space if shielded from direct radiation, and some spores can survive even without much protection for shorter periods. But the leap from years to millions of years is enormous. Even with shielding, the constant rain of high-energy particles in interstellar space would gradually break down complex molecules, including the structures inside living cells. It's not impossible that some could survive, especially if buried deep enough in a protective layer of ice or rock, but the odds would shrink with time. In that sense, the most realistic version of panspermia is not the direct transport of living organisms, but the spread of the molecular precursors, chemicals that, given the right conditions, could help life get started. That's where bodies like 3I Atlas come in. If they can preserve those chemicals over vast distances and deliver them intact to new environments, they could play a role in seeding planets with the raw materials for life. The delivery could happen through a gentle impact on a planet with an atmosphere and oceans, or through breakup in that planet's atmosphere, scattering fragments across the surface. In our own solar system, we know that comets and asteroids have struck Earth countless times, and some of those impacts likely brought organics along for the ride. If the same process happens on other worlds, then interstellar objects might help spread these vital ingredients far beyond their birthplaces. The idea becomes even more interesting when you think about the scale of time and space involved. Our galaxy contains hundreds of billions of stars, many of them with planetary systems. Over the history of the Milky Way, countless comets, asteroids and planet fragments have been ejected from those systems into interstellar space. A small fraction of them will, by chance, pass close enough to other stars to be pulled in. Some will strike planets or moons. Each such event is an opportunity to deliver something new: minerals, metals, volatiles and perhaps organics. Over billions of years, the cumulative effect could be a galaxy-wide mixing of materials, a slow but steady exchange that blurs the lines between the histories of different worlds. From that perspective, 3i Atlas is not just an isolated visitor. It's a representative of a much larger population of wanderers, each carrying a sample of its home system's chemistry. The fact that we can detect it at all means that there are probably many more we never see, ones that pass too far from the sun to brighten enough for our telescopes, or ones that slip past while our surveys are looking elsewhere. Each of those invisible travellers could be part of the same quiet process, a process that might have been happening since before Earth was even born. When we talk about seeding life, it's easy to imagine something deliberate, an engineered probe carrying genetic material or microorganisms sent with intent. That's one possible scenario, but the version scientists usually consider for Panspermia doesn't require purpose. It's simply the byproduct of planetary systems forming, evolving, and interacting with their environments. Planets collide. Comets are flung outward by gravitational encounters. Asteroids are broken apart by impacts. The fragments scatter, and some of them leave their home stars forever. The galaxy's natural dynamics do the rest. It's also worth noting that if the process works one way, it works both ways, just as 3i Atlas could, in theory, deliver materials from another star to our solar system. Debris from our own system could be travelling elsewhere right now. Impacts on Earth, Mars, or the moons of the outer planets could eject fragments into space. Most will stay bound to the sun, but some could reach escape velocity and drift between the stars. If any of those fragments carried microbes or organic-rich material, they could someday end up in another system entirely. In this way, the seeding process is not just something we might receive, it's something we might also contribute to. The reality of detecting such a process is much harder. Even if we could sample 3i Atlas directly and find complex organics, proving that they were formed in another star's system rather than in our own solar system's environment would require precise chemical and isotopic analysis. Those differences might be detectable in a lab, but without a sample return mission, we can only guess based on the faint clues in its light spectrum. And even if we did find such differences, proving that they had any role in starting life anywhere would be an even greater challenge. It's one of those ideas that may remain more plausible than provable for a long time to come. Still, it's an idea that reshapes how we think about life's place in the cosmos. If life's raw materials can move between worlds, then the starting conditions for biology may be more widespread than we've imagined. Life might still be rare, depending on how often those materials encounter planets with the right conditions, but it wouldn't be isolated. The chemistry of one system could, over eons, become part of another, and so on, until the galaxy is a vast network of shared elements and compounds. When we look at 3i Atlas through that lens, it becomes more than just an astronomical curiosity. It becomes part of a story that connects distant suns, young worlds, and the possibility of a life emerging in places we'll never see. It's a reminder that even a small, faint object drifting through the dark can carry something profound, a connection, however tiny, between one corner of the galaxy and another. If an object like 3i Atlas could carry the raw ingredients for life, the only way we could know without touching it is to study the light it reflects and emits. Light is our most versatile tool for decoding chemistry at a distance, because each element and molecule interacts with it in a unique way. When sunlight strikes the surface of an object or passes through the gases it releases, some wavelengths are absorbed while others are reflected or re-emitted. Those changes leave patterns, spectral fingerprints, that can reveal the composition of the object to anyone who knows how to read them. For 3 Atlas, the challenge began with its faintness. Even at its brightest, it was barely visible to large telescopes, and the presence of a coma meant that light from its solid surface was mingled with light scattered from tiny dust grains and gas molecules surrounding it. That blending complicates the process of identifying specific features in its spectrum. Still, observers took every opportunity to collect data, knowing that once it moved farther from the Sun, it would fade quickly beyond the reach of our instruments. The spectra showed the expected broad features of dust reflecting sunlight, overlaid with more subtle signals from the coma. In the visible range, the dust appeared to have a reddish tint, something we see in many comets both in and beyond our solar system. That red slope is usually caused by complex organic compounds on the surfaces of the dust grains, long-chain molecules that form through the slow action of cosmic rays and ultraviolet light on simpler ices and hydrocarbons. It's the same kind of material we've detected on the surfaces of many icy bodies in the Kuiper Belt and in meteorites that have fallen to Earth. In the near-infrared, some weak absorption features hinted at the presence of water ice, though the signals were faint. Water is one of the most common volatile substances in comets, so its presence wouldn't be surprising, but confirming it in such a distant, faint object is never easy. In this case, the detection was consistent with a small amount of exposed ice being heated and sublimating into the coma, releasing both water vapour and entrained dust. That activity could explain the modest size of the coma we saw, a steady but not dramatic outflow. Other spectral features suggested the presence of carbon-based molecules, perhaps in the form of simple volatiles like carbon monoxide or carbon dioxide. These molecules are more volatile than water ice, meaning they can sublimate at lower temperatures, even in the outer solar system. If they were present, they could have contributed to the object's activity before it came very close to the Sun. This might also explain why 3I Atlas began showing a coma earlier than expected. It may have started venting carbon-rich gases while still far from us, powered by sunlight that barely warmed its surface. One of the subtler goals of these measurements was to look for chemical differences between 3I Atlas and comets that formed in our own solar system. Even small shifts in the ratios of certain isotopes, different forms of the same element, can tell us something about the environment in which the object formed. For example, the ratio of heavy to light hydrogen, deuterium to hydrogen, in water ice is one of the key indicators scientists use to compare comets. Unfortunately, detecting those ratios in an object this faint at this distance was beyond our reach. The data we collected was enough to confirm general similarities, but not precise enough to say whether its isotopic composition matched anything we know. Still, even these partial results have value. If its chemistry is broadly similar to that of our comets, that tells us something important, that the processes forming such bodies around other stars can produce materials much like our own. If there are differences, they may be subtle enough that only a close encounter or a sample return mission could reveal them. Either way, it reinforces the idea that planetary systems across the galaxy may share more common ground than we once assumed. The reddish organics are especially interesting because their formation doesn't require life, it's a purely chemical process, but they can serve as the foundation for more complex chemistry under the right conditions. We've seen these complex organics not only in comets, but also in the atmospheres of moons like Titan, where they create thick hazes and contribute to a rich chemistry that continues to evolve. If 3I Atlas formed in a region of its home system similar to our outer solar system, it might have spent billions of years in cold storage, preserving those organics until its ejection. That would make it a time capsule of early chemistry from another star's neighbourhood. There's also the question of what we didn't see. No obvious signatures of unusual metals, no strange reflective coatings, no spectral lines that would hint at industrial or manufactured substances. That absence is consistent with a natural body, though it's worth noting that not all materials, natural or artificial, are easy to detect at these distances. For now, the chemistry we can confirm fits well with the idea of a dusty, icy nucleus, shedding a modest amount of gas and particles as it warmed. It's tempting to think of spectroscopy as a definitive tool, something that can tell us exactly what's there, but in reality it's a bit like overhearing fragments of a conversation in a crowded room. You catch enough words to know the topic, but the full story remains just out of reach. For 3i Atlas, the words we caught point toward a familiar set of materials: water, carbon compounds, dust grains coated with organics. They hint at a long, quiet history in deep space, with occasional bursts of activity when conditions allowed. All of that fits neatly with the picture of an interstellar comet, but the real fascination lies in imagining the specifics of its origin. What star once warmed it? Did it form in the outskirts of a planetary system like our own, beyond a frost line where ices could remain stable? Was it nudged into a new orbit by a migrating planet, slowly drawn inward until a close encounter hurled it into interstellar space? Each of those steps would leave its mark in the chemistry, in ways subtle enough that only by collecting far more data, or someday a sample, could we read them fully. Until then, we're left with the spectral hints and the knowledge that in those faint lines and slopes is a direct connection to a place we can't visit. Every atom in 3 Atlas's dust and ice was assembled somewhere else in the galaxy, under conditions we can only guess at. Every complex molecule has endured the cold and the dark for longer than humanity has existed. The fact that we can even begin to read that history from millions of kilometers away is a testament to the precision of our tools and the patience of the people who use them. Every object that enters our solar system on a hyperbolic path has one thing in common: it's only visiting. The sun's gravity slows it down, bends its trajectory, and then releases it again, sending it back into the deep at a different angle than the one it arrived from. For 3i Atlas, this moment is already playing out. Its closest approach to the sun is behind it now, and the sunlight that warmed its surface and coaxed out its faint coma is steadily fading. The arc of its path has turned outward, away from the warmth, back toward the places where sunlight becomes little more than a pale suggestion. Tracking that path is a matter of precision. Even the smallest uncertainties in early observations can magnify over time, shifting projected positions by millions of kilometers. That's why astronomers work quickly after discovery to secure as many measurements as possible, locking down the exact timing and location of the object across multiple nights. The more data they have, the better they can fit the orbit. For 3i Atlas, those efforts paid off, giving us a clear picture of where it's been and where it's going. Its exit trajectory carries it upward out of the plane of the planets, tilted at a steep angle relative to the ecliptic. That angle alone tells us something. It's not part of the flattened, disc-like structure of our solar system's regular population of comets and asteroids. Instead, it's cutting across that disk at an angle that only an interstellar origin can explain. If you were to draw the solar system as a flat sheet with the planets moving along its surface, 3i Atlas would be a pebble skipping off the sheet, heading out into the three-dimensional depth of space. As it travels, its speed will settle into something close to what it had before entering. Tens of kilometers per second relative to the sun. That's more than fast enough to escape permanently, even accounting for the slight pull of gravity from planets it passes near. In fact, by the time it leaves the sphere of the sun's influence, it will be moving faster than most of the stars in our local neighborhood relative to one another. That speed will carry it far beyond the outermost regions of our solar system, past the imagined boundary of the Oort cloud, and into the interstellar medium once more. The question of where it's going next is more complicated than simply drawing a straight line. The galaxy is not static. Stars move, spiral arms rotate, and gravitational tides from the Milky Way's mass distribution constantly shift the positions of everything in it. If you tried to trace 3i Atlas's course forward for a few million years, you have to account for the fact that the stars it might pass near in the future are themselves moving on their own orbits. What looks like an empty path now might intersect with a star system later, and what seems like a near miss could widen into empty space. Some early calculations suggest that after leaving our neighborhood, 3i Atlas will head toward a region of the galaxy sparsely populated by nearby stars. It's unlikely to pass close enough to any of them to be captured, at least in the near term, but over timescales of tens or hundreds of millions of years, the odds increase that it will drift within range of another system's gravity. If that happens, it might end up looping through that system the way it did ours, perhaps shedding a little more dust and ice before moving on again. It's also possible that it will never come close enough to another star to be significantly affected, wandering instead in the interstellar medium until the end of its existence. That environment is not entirely empty. It contains sparse gas, dust, and occasional high-energy particles, but it's so thin that an object like 3I Atlas could travel for billions of years without suffering much change in its overall structure. Over such vast timescales, the most significant changes would come from cosmic rays, slowly altering its surface chemistry, and from the very occasional micrometeorite impact. The exit path also offers a kind of closure to the story of its brief visit here. Once it fades beyond the reach of even our largest telescopes, it will join the uncountable number of small, dark objects in interstellar space, most of them never seen by any observer. The difference is that for this one, we've had a chance to watch, to measure, to add it to the growing catalogue of interstellar visitors. The next time it passes near a star, it might be studied again by someone else, in some other system, who will see it as a newcomer from far away. They won't know that we once did the same, and while its trajectory is taking it away from us forever, it's worth remembering that the information we've gathered remains. Its orbit is a record not just of its path, but of the gravitational nudges it received here, subtle shifts in speed and direction caused by passing near Earth's orbit, or by the faint pull of Jupiter from afar. These changes, though tiny, are enough to make this segment of its journey unique, different from any other stretch it has travelled. In that way, even our solar system leaves a signature on it, one that will persist for as long as the object exists. The outbound leg is also a reminder of how fleeting our opportunities for close study are. Had 3I Atlas been discovered even a few months later, much of the detailed observation we managed would have been impossible. By the time it moves beyond the reach of our current instruments, the coma will have long since faded, the nucleus will reflect only the dimmest sunlight, and the signals we might have studied will be lost in the background. This urgency is what drives astronomers to push for faster, more automated survey systems, tools that can spot these visitors earlier and track them longer. In the grand scheme, its departure is simply the continuation of a journey it has been on for untold ages. It may have spent hundreds of millions of years in interstellar space before arriving here, and it will likely spend just as long or longer before its next encounter with a star. The fraction of that time it spent within reach of our telescopes is so small it barely registers on the scale of its life, but for us, it's a rare and significant moment. We've intercepted it in transit, glimpsed its nature, and now watched it recede into the same vastness it came from. From here, it will continue outward, growing colder as the sun shrinks behind it into a bright point. The coma will vanish entirely, and any exposed ice will refreeze under the deep chill of space. The slow spin we've measured will go on, turning the same faces to the darkness over and over. Perhaps in some distant epoch, it will feel the faint tug of another sun, another set of planets, another group of watchers curious about what it is and where it came from. Until then, it will remain one more quiet traveller in the galaxy's endless migration of small bodies, carrying with it the hidden record of its origin, its time here, and all the miles still ahead. The moment an object like 3I Atlas appears in our records, it changes something in the way we think about the sky. We're used to seeing the planets, the moon, the familiar constellations, even the slow drift of near-Earth asteroids. They're part of the repeating scenery, bound to the sun, moving in predictable cycles. An interstellar visitor is none of those things. It is not part of our system's choreography, and it does not repeat its steps. It comes once, on a trajectory we can plot but never retrace, carrying with it a history we can't reconstruct in full. The knowledge that we will never see it again adds a weight to the experience of observing it. In those brief weeks or months when the data is coming in, it becomes a point of focus for a large part of the astronomical community. Telescope schedules are reshuffled, observing proposals are revised, and a global network of professionals and amateurs turns its attention toward this single, faint speck. The images that result are sometimes little more than streaks of light against a background of stars, but each streak holds information about its motion, its brightness, its behaviour. Each one is a record of a moment when it was still close enough to study. That closeness is always temporary. As soon as it's spotted, it's already moving away from the discovery point, and every night the geometry changes. The light we receive reflects not only the properties of the object itself, but also the constantly shifting angle between it, the sun, and Earth. That means the window for certain kinds of measurements is short. You might have just a handful of opportunities to catch it under the right conditions for spectroscopy, or to watch the coma and tail under favourable illumination. Once those opportunities pass, they can't be recreated. This is where the idea of a glimpse becomes more than a poetic phrase. In practical terms, it's the reality of what's possible when something passes by at interstellar speeds. Even with the best instruments we have and the coordination of observatories around the world, we can't slow it down or bring it back. All we can do is make the most of the time we have, collecting as much data as possible before it fades beyond reach. The reward is knowing that every spectrum, every image, every brightness curve will be studied for years afterward, long after the object itself has disappeared into the background. The value of that data isn't just in the specifics it reveals about this one object. It's also in what it adds to the broader picture of interstellar material. When we compare 3i Atlas to Oumuamua and Borisov, or to any future visitors we find, patterns will emerge. Patterns we couldn't see if we had only one example. Those patterns can help answer questions about how common certain types of material are in the galaxy, how they're distributed, and how they change over time. Even the absence of certain features can be informative, if, for example, none of the interstellar objects we've observed so far show signs of a large-scale artificial construction. That tells us something about the rarity of such structures, at least among bodies of this size and type. Beyond the scientific value, there's the impact these visitors have on our sense of place. For most people, space is an abstract concept, vast, distant and disconnected from daily life. But when you know that a small physical piece of another star system is passing close enough to be seen in a telescope, it changes that perception. It becomes tangible. You can point to a spot in the sky and say, that's from somewhere else entirely. It's not a theory, not a simulation, but an actual object on an actual path that began far beyond our sun's influence. That awareness can make the sky feel larger and smaller at the same time. Larger because it reminds us of the distances involved, millions or billions of years of travel through empty space. Smaller because it shows that those distances are not absolute barriers. Material moves between systems. Our solar system is not sealed off. It's part of a larger web of exchange, where objects come and go across the galaxy. We might not notice most of them, but the few we do see are proof that the connections exist. In a way, the fleeting nature of the encounter makes it more powerful. We live in an age where so much of the universe can be revisited at will. Images of the Moon, Mars, distant galaxies are stored and can be called up instantly. But an interstellar visitor like 3i Atlas doesn't give us that luxury. It comes once. The photographs and spectra we capture are final in a way that few other astronomical records are. They are the complete archive of that object's time here. Whatever else it does, wherever else it goes, we won't see it again. That fact adds urgency to the work and a certain intimacy to the observation. For the scientists involved, there's also the knowledge that their measurements could turn out to be more important in the future than they seem at the time. A new theory about interstellar objects developed decades from now might depend on having a reliable data set from something like 3i Atlas. A detail in the spectrum that seems insignificant today could become a key clue when compared to the results from a much larger survey years down the line. In that sense, every glimpse is an investment in the science of the future, and then there's the human side of curiosity. Long before we had telescopes, the idea of something arriving from the stars captured imagination. stories about messengers from the heavens, omens in the sky, and celestial travellers appear in many cultures. Now that we can actually detect such travellers, the reality is quieter but no less intriguing. Instead of fiery portents, we see faint specks on a screen, but those specks are real, and they carry stories written in their chemistry and motion. The gift in all of this is not just the data, but the reminder that we're part of a dynamic galaxy. Things happen here. Objects arrive, pass through, and leave, each carrying with it a history that's longer than our species has existed. Most of the time, we're not watching, and those events unfold unnoticed. But every so often our instruments catch one, and for a little while we get to witness a connection across the void. That's the glimpse, the brief intersection of two vastly different journeys, ours and the object's, before each continues on its own path. The fact that such moments are rare makes them worth more. And it's not just the scientists who get to share in it. Many of these objects are bright enough, at least for a short while, to be seen by skilled amateur astronomers. That means anyone with the right equipment and clear skies can look up and see the same thing being studied in professional observatories halfway around the world. In that way, the glimpse becomes communal, shared across borders and languages, connected only by the common act of pointing a telescope toward the same coordinates. Once 3i Atlas is gone from view, it will live on in the data and in the memory of having seen it. We'll know its path, its approximate size and composition, its behaviour near the sun. We'll know just enough to understand how much more there is to learn and to be ready for the next time an interstellar visitor appears in our sky. And when that next one comes, and it will, we'll look back at this glimpse as part of the foundation that lets us recognise, study and appreciate it even more. When something like 3i Atlas passes out of sight, it doesn't happen all at once. There's no single night when the entire world looks up and watches it vanish. Instead, the moment is staggered. For some observers, it slips away weeks before others lose it. A telescope in the southern hemisphere might catch it for a few nights after the northern instruments can no longer track it. Larger observatories can follow it until its light drops below thresholds that would be invisible to smaller lenses. And even then, long exposures on sensitive detectors might continue to record its presence, though by then it's no more than a few faint pixels against the background. Those final observations are different in tone from the rush of early discovery. When the object is first found, there's urgency, a scramble to measure everything possible before it changes too much or becomes too distant. As it begins to leave, the pace slows. The data is still important, but the range of what can be measured narrows. Coma activity fades. The spectrum becomes harder to read as the signal weakens. What's left is mainly positional tracking, pinning down its coordinates so the orbit is defined with precision. Even these late measurements matter, because they refine our understanding of its path and help us predict its position far into the future, long after we can no longer see it. There's a certain quiet that settles in during this stage. The discovery has been announced, the key data collected, the comparisons with other objects begun. The most detailed papers are still months or years away, but the real-time excitement is tapering. For the people who have been following it closely, this can be a bittersweet time. There's satisfaction in having done the work, in having captured the object's brief presence in our skies, but also a recognition that the opportunity is ending. You can point your telescope at the same patch of space a week later, and the difference will be obvious. Not in what you see, because you might not see it at all, but in what you feel. The connection is slipping. Some observers mark these moments quietly, with no formal acknowledgement beyond the last recorded exposure. Others note them in personal logs, as a way of remembering the time they spent tracking it. For amateur astronomers who devoted hours to following 3i Atlas, the farewell might come on a cold, clear night when they realise the signal has fallen below what their equipment can detect. They know it's still out there, moving away, but for them, the practical part of the encounter is over. Professionals too have their own sense of closure. The observing runs get shorter, the scheduling less urgent, until eventually there's nothing left to assign. Other targets take priority. The interstellar visitor becomes part of the archive, no longer a current event but a completed observation. From here on, the story continues only in analysis and in whatever the data reveals under closer examination. Even so, there's a human tendency to imagine it still passing overhead, even when it's far too faint to see. Its position changes steadily, night after night, as it moves outward. Charts can tell you where it is, how far it's travelled since discovery, how fast it's moving now. Knowing those numbers can make it easier to picture, as though the mind fills in what the eye can't capture. You can look up at the sky in the direction of its path and think of it there, shrinking into the distance. There's something grounding about this kind of farewell. It's not dramatic. There's no sudden disappearance, no abrupt end. Instead, it's the gradual acceptance that this encounter, like all encounters with interstellar objects, was temporary. The reality of their speed and trajectory means we don't get second chances. The only permanence is in the records we keep, the spectra, the images, the orbital calculations. Those are the pieces that remain, long after the object itself is beyond reach. That doesn't make it meaningless. If anything, the temporary nature of the encounter is what gives it weight. The act of saying goodbye to something like Three-Eye Atlas is really an acknowledgement of what it represents. A connection to another part of the galaxy, however brief. Its origin is still unknown, its full story out of reach. But for a short while, its path intersected ours, and we were here to notice. It's worth remembering that this farewell is only one small moment in its much longer journey. It has been travelling for millions of years, perhaps since before Earth had life, and it will continue for millions more. Our role in its history is almost negligible. We are one brief line in its timeline, a point of contact so short that it would barely be visible if its life were drawn out on a cosmic scale. And yet, for us, it was significant enough to track, to measure, to write about. That's the way perspective works. What is small on one scale can be large on another. For those who work in astronomy, these partings are not rare. Comets come and go, asteroids pass by, distant stars flare and fade. But interstellar visitors are still uncommon enough to stand apart. Each one carries the possibility of being unlike anything we've seen before. The farewell, then, is not just to the object, but to the set of opportunities it brought, the specific chance to compare it to other known bodies, to test theories, to refine methods. Once it's gone, that exact opportunity will never come again. Even after the object is gone from sight, the conversation about it continues. Data is shared across research teams, results are compared, and theories are revised. The observations are folded into broader studies, influencing how astronomers design surveys and what they prioritise in the next search. In that sense, the farewell is only to the direct contact. The influence of the encounter lingers in the choices that follow. For some, there's also a personal dimension to these endings. The people who discovered it, who stayed up through cold nights gathering data, who adjusted plans and schedules to follow it, many of them will carry a kind of private connection to it. They might remember exactly where they were when they first saw the detection images, or how it felt to lock the telescope onto it for the first time. Those memories become part of their own history in astronomy, tied to one particular object among the countless others they've observed. By the time Three-Eye Atlas has moved too far and too faint for any instrument we have to detect, it will be well on its way toward a region of space where no human eyes will follow it. The sunlight that reflects from its surface will grow weaker until it's lost in the black. It will travel alone again, as it did before it crossed paths with our solar system, carrying with it the dust and ice and chemistry that formed in a place we have never seen. And in the records we've kept, its brief appearance here will remain, a fixed point in the ever-changing flow of things that pass through our skies. The farewell under the stars is, in the end, as much about us as it is about the object. It's a reminder of the limits of our reach, of the patience needed to wait for the next encounter, and of the value in paying attention when those encounters happen. We can't follow it beyond the faintest edge of our instruments, but we can hold on to the knowledge that we met it, that for a small span of time our paths crossed and we were here to watch it go. And now, with our visitor far beyond sight, the night feels a little quieter. Somewhere out there, 3i Atlas is continuing its journey, unchanged by the fact that we were here to watch it pass. The data is stored, the images saved, the orbit mapped. What remains now is the space it leaves behind, and the thought that at any moment another traveller might be on its way toward us, already crossing the gulf between stars. If you've stayed with me through this long exploration, thank you for sharing this moment in time. I hope the pace and the quiet have given you a sense of calm, even as we've wandered through such distant ideas. If you'd like to join me again the next time we look into the dark and find something unexpected there, you can follow along here. Until then, may your nights be clear, your thoughts steady, and your rest deep.